Chrome permission to share. Okay, I need to come back, like quit and log back
Yeah,
in
yeah,
order to
please.
do that. Yeah, sorry about that.
Yeah, please.
Hello, hi. I'm back. Could you are you able to see my presentation?
No, not yet. No, not yet.
Mm, mm. Let's see. Does this work? Do you see my presentation yet?
Yeah.
Okay, sounds good. Okay, let's see. I think there might be a bit of a lag, you know, from US to India, so there might be a bit of a few seconds lag. Um, so I'll try to follow it. Okay. Good evening, everybody. Thanks for coming to my talk, and thanks to Professor Kumar for the invitation. What I'm going to present about is kind of a work that I started with my advisor, Debashish Mondal, when we were both at University of Chicago. And since then, I have extended the work with my ex-PhD students, Subrata Pal and Ani Pathak, and our research assistant, Hongwon Wang. So in this project, we're talking about sampling from the conditional distribution of Gaussian, high-dimensional Gaussian variables. So if you're the size of the problems I'll be talking about involves lakhs or millions of Gaussian random variables, not a few hundred. So for a few hundred, there are when the dimension of these Gaussian distributions are within 100 or even nowadays within 1,000, the standard algorithms, standard methods would work. But beyond that, when the dimension of the number of variables is in the lakhs or millions, standard methods won't work, and that's where we have some innovation. So let's think about a few cases of high-dimensional Gaussian simulation. One of these, the most popular case arises from the Gaussian mixed linear models, where we have the response vector y, um, covariate matrix X with coefficients beta, and there could be some other random effects psi with an incidence matrix F, and Gaussian errors or normal errors epsilon. So here, if beta also follows a normal distribution with the inverse covariance matrix R1, so that the covariance matrix is R1 inverse. And if psi also follows a normal distribution with mean zero and a covariance matrix R2 inverse, and epsilon, as usual, follows normal distribution with mean zero and a covariance matrix, which is 1 over lambda 1 times the identity, where lambda 1 is the precision parameter, or 1 over lambda 1 is the variance parameter. Um, Under these sort of assumptions, it can be shown that the joint distribution, conditional distribution of beta and psi, given the data y, has a Gaussian distribution whose mean is A inverse B, and the covariance matrix is A inverse where B is this vector lambda 1 X transpose Y and lambda 1 F transpose Y, and A is a covariance matrix. A is a precision matrix or inverse covariance matrix given by lambda 1 times X transpose X, X transpose F, and F transpose X, F transpose F, plus the block diagonal matrix with blocks R1 and R2. This is why I parameterized everything in terms of the precision parameters. Then these matrix A and the vector B, they look simple. Otherwise, if I had followed the usual covariance matrix parameterizations, there would have been a lot of inverses here. So in many modern applications, what happens is that the matrices X, F, R1, R2, they're typically, they could be very high dimensional, but they often have structures. For example, they could be sparse matrices. A sparse matrix is a matrix most of whose entries are zeros. So those are nice matrix because we don't need to really store the zeros. If we know, um, we just need to store the locations of the zeros, and well, not even that. We just need to store the non-zero entries and their locations. Then uh, it's it can be stored in a much compressed memory format. For example, in very high dimensional Gaussian regression, X can be where X could be like a genetic matrix where the number of columns in X would be in the millions, corresponding to number of single nucleotide polymorphisms in species. In spatial models with millions of locations, the random effect psi could be a very high dimensional Gaussian random field. And the matrix F, in this incidence matrix F, could be a very sparse matrix, indicating whether there is you know, there's an observation or not in a cell. But how do high dimensional Gaussian distribution, high dimensional mixed linear models are not the only case where the Gaussian simulation arises. Other examples also exist in um, generalized linear models. A very easy example would be the probit regression, binary probit regression through the conjugacy through latent variable representation. Another slightly less obvious example would be logistic regression. So binomial logistic regression. It is well known that if we have observations yi from either Bernoulli pi I, or they could also be binomial with more than one number of trials. And here we assume that the logit of pi I has a linear form xi transpose beta plus fi transpose psi, where beta follows a Gaussian multivariate Gaussian distribution as before, and psi follows also my multivariate Gaussian distribution. Then generally, if we just write down directly the full posterior distribution, it doesn't have a conjugate, it doesn't have a nice structure. But in 2013, Nick Paulson and his colleagues showed that we can introduce these missing variables or latent variables, omega I, which they defined as polygamma vector random variables. So after introducing these polygamma random variables, um, the full conditional distribution of beta and psi given y and also this w, they again admit a conjugate multivariate Gaussian distribution with a very similar structure like before. We have the mean as A inverse B and the covariance matrix A inverse, where B is X transpose kappa and F transpose kappa. And kappas are nothing but yi minus half. If there are more than one number of trials, you will have to adjust for that. But they're basically the transformed responses. Um, and A again is this matrix X transpose omega X, X transpose omega F, F transpose omega X, and F transpose omega F, plus the block diagonal R1 and R2. Here, omega is a diagonal matrix. So in the previous case, omega was simply homoscedastic diagonal, meaning it was lambda 1 times the identity. Here we have slightly more complicated version. It's a diagonal with omega 1 through omega n. but nevertheless, diagonal matrices are very nice. So it has, again, a very similar form like before. And traditionally, what we have learned, the way we should simulate from multivariate Gaussian distribution is through matrix factorizations. You may take a Cholesky factorization of the inverse covariance matrix, or a um, eigenvalue decomposition of the inverse covariance matrix. And using those factors, you could simulate from these multivariate Gaussian distributions. However, those methods suffer from something called curse of dimensionality. That is, their storage scales as n squared, number of variables squared of number of variables, and the number of floating point operations, which characterizes the computational complexity of the time needed, that scales in the cubic order of the number of the dimension. So if n is the number of variables in this joint distribution, then the storage requirements would be order of n squared, and the computational complexity will be order of n cube. For few, tens or hundreds, or even nowadays with our powerful computers, even 1,000 dimensions, that's not a problem. The problem happens when you have millions, 100 lakh, hundreds of thousands, or millions of such random variables. Now, when the number of observations, there's it's like a million or something, you would need terabytes of RAM just to store the covariance matrix. And most standard computers do not have terabytes of RAM. And even if you had a terabytes of RAM, for example, those powerful workstation or supercomputers or those clusters, factorizing those covariance matrices using Cholesky decomposition or singular value decomposition or the eigenvalue decomposition, they would take actually months or years, honestly. So it's absolutely impossible to use those brute force matrix decomposition methods to simulate from very high dimensional Gaussian distributions. So this is where our innovation comes in, and again, because it's a it's sort of a specialized algorithm. So Cholesky decomposition and the spectral decomposition, those are universal algorithms. If they work, they would work for any problem. But for high dimensional problems, they are not computationally feasible. The methods that we are going to propose, they're quite broad. They would not work for all sorts of problems, but as I will discuss, they do work for a very broad class of problems for which high dimensional Gaussian distribution arise quite frequently. And the proposed algorithm is based on very simple tools that, for example, I learned in my undergrad at ISI. So, multivariate statistics course, the first one, I think it was a linear algebra course, um, where we learned that if you have two matrices A1 and A2, they have the same n rows, but maybe may have different number of columns. And if V1 and V2 are standard multivariate Gaussian random vectors, meaning their components are ID normal 0, 1, and are of appropriate dimensions so that you can take A1 times V1 and you can take A2 times V2, then this vector eta, which is B plus A1 V1 plus A2 V2, it follows a normal distribution with mean B, which comes from this fixed part B, and the covariance matrix A, where A is of the form A1 transpose plus A2 transpose. And obviously, if you have more than two matrices, A1, A2, A3, similarly, you can keep on expanding this matrix A. Now, the interesting observation that I also learned there is that if you solve the system of equations Ax equals to eta, it will follow, eta will follow, sorry, not eta, X will follow the distribution A inverse B, and the covariance matrix, that would be A inverse times A inverse. Well, that's just A inverse. So 2 steps is that we first simulate from a Gaussian distribution where the mean is B and the covariance matrix is A. But then somehow we solve this system of linear equations, x equals to eta, and that solution follows the desired form, has the desired form. It has the mean A inverse B and the covariance matrix A inverse. In many problems, as we will see, there are structures that this matrix A, A1, A2, they are matrix-free operators. But by matrix-free operators, I mean that ultimately matrices are just representations of linear operators with respect to the standard Euclidean basis. But there are results that if you express them in using a different basis, you can compute such a vector, the linear operator, in a much easier way. So I'm calling the matrix-free operator in the sense that, generally in the sense that, if you give me a vector v, or v1 or v2, I could compute this matrix vector products, av, or a1 v1, or a2 v2. I can compute them using at most order of n storage in RAM and in less than order of n log n computational complexity. A few examples of those would be, for example, if the matrices A, A1, A2 are sparse matrices. For example, if they're diagonal matrices, that's very easy, right? If you need to multiply a diagonal matrix with a vector, well, you really don't need to multiply with the zeros, just take the element-wise product with the diagonal and you're done. If they're sparse matrix, which are slightly more complex than diagonal matrices, there are lots of zeros, then you don't, in this arithmetic, you don't need really, 0 times anything is 0. So you don't need to multiply those. You can save on computation. Ultimately, you get order of n log n computation, less than order of n log n computational complexity. A more non-trivial example would be operators like fast Fourier transformation or discrete cosine transformations. There are results that says that you can do those computations recursively so that if I give you a vector v, you can compute its fast Fourier transformation or discrete cosine or trigonometric, basically the discrete trigonometric transformations in order of n log n computational complexity. And you really don't need to store those Fourier basis matrix because they have very simple structures. Now, then we need to still solve the system of equations x equals to eta. However, how do we solve those equations, right? So we need to be able to solve this equation is little order of n cubed computational complexity. So
Doctor,
fast forward to, yeah, 5 minutes.
yeah, you have 5, 6 more minutes.
Yeah, I will try to just present the algorithm. Sounds good. Thank you. So fast forward to 2011, before that, I only learned about Gauss-Seidel method or Gaussian elimination methods, which are again not matrix-free. You need to store the entire matrix to be able to compute these, solve the system of equations. Fast forward to 2011, I learned about the conjugate gradient algorithm, which is a very old algorithm from Seifel in 1951. And it's an iterative algorithm. Basically, what it does, it constructs a basis of the column space of A using conjugate vectors, which are orthogonal in the inner product defined by A, and then just simply takes the, because every vector has a basis expansion for any basis in the Euclidean domain, you can take the, you can expand them using those bases. And you can take the coefficients, compute the coefficients easily. Ultimately, what it does, it's an iterative algorithm, um, which only involves the matrix A or the operator A through this matrix vector multiplication. The only way the matrix or the operator A arises in this algorithm is through matrix vector multiplication. And it converges very fast, typically enough, only a few iterations. You really don't need to take a lot of iterations. So the conjugate gradient algorithm provides a fast matrix-free method of solving system of linear equations where you can compute matrix vector product A times U in a cheap manner. I will just talk about one example then, Gaussian Markov random fields, where such a representation appears. So Gaussian Markov random fields, for example, shown here, has many nodes. Here, for example, I show only 5, and there are weights for every edge. And you can take a um, matrix S whose number of rows is the number of vertices and number of columns is number of edges. And in for every column, the only two non-zero entries are the square roots and on the negative of the square roots of the weights between those two edges. So ultimately, this matrix is a very sparse matrix, only two non-zero entries per column. And these there is you can show that this matrix times its transpose gives the inverse covariance matrix of the Gaussian Markov random field for any Gaussian Markov random fields. So this gives a rectangular decomposition, like so it gives you gives a method to compute similar vector from BA and then solve the equation. Um, and so I will just go to one simulation study. So for example, here I simulated data on a 1024 by 1024 grid, and I have 50% of the grid cell observed. Now, this is the data is generated from an exponential covariance model, and I'm trying to conditionally simulate at all the observations given the data. And for comparisons, I compare with two other approaches: the Vecchi approximation, the GPGP algorithm, and then the NGP algorithm. Both are Vecchi approximations and of the graph. And what we saw is that the GPGP approach is very slow. It takes 160 seconds per draw. NNGP is faster, but it still takes around 8,000 seconds. That's roughly more than 2 hours for every 1,000 draws. But the proposed method using the Fourier transformation and uh, the spectral decomposition, not the spectral, sorry, the Fourier domain, the fast Fourier transformation, excuse me, takes less than, takes only 103 seconds per 1,000 draws. So that's 0.1 second per draw. So these are immensely faster than the standard algorithms available. So I'll stop there. Thank you. I have other examples, but I don't have time to go over those. But I'll be happy to talk about them later. Thank you.
So now it's a time for some questions and discussions. So anybody have any questions can ask now. Uh, okay.
Sir, shall I ask
Uh,
one question?
yeah, yeah.
Sir, you are mentioning that if the matrix is sparse, then this reduces the complexities. But if the matrix is of full order, assuming that almost uh, say something like 90% of the positions are filled, then in that
Right.
case, will this be effective time using?
That's a very good question. So the general answer is no, if there is no other structure in the matrices. But most of the times, such large, dense matrices appear, for example, in spatial statistics through some covariance functions. And you have certain structure for those covariance function. For example, for fractional Gaussian fields, the covariance matrix is diagonalizable by fast Fourier or the discrete cosine transformations. Does that make sense? So although there are lots of non-zero entries, but the eigenvalues analytically and the eigenvectors form the fast Fourier basis of the real domain. And you can again then do matrix vector multiplication using this fast Fourier transformation. Does that
Okay.
answer your question?
Yeah, I can follow. I can understand. And one more question. See, the classical decomposition structures like Cholesky's decomposition and uh, eigenroots way of doing things, and you are suggesting fast Fourier, saying that it works very fast and very okay, or very effectively in some sense. A reduction in memory consumption, something of that sort. But it's okay, but in what way or what feature of fast Fourier is able to capture the pattern quickly? Can you make it little bit
Right. So
explain?
Yeah, that's another very good question. So fast Fourier transformation, if you want to take a fast Fourier transformation of a vector, typically, if the vector is highly composite, meaning the length is product of lots of small primes, you can take the fast Fourier transformations recursively on smaller and smaller length vectors. That makes it faster. So I cannot go into the details of that, but that's those are results, very standard results in engineer in what you call it in signal processing. Um, that the
Okay, the
number of
recursion,
floating point operations is much faster.
the recursion is the key. That's what you are trying to emphasize.
The recursion is the key. Yes,
Thank you, sir.
recursion and period is, yeah.
Thank you very much for your insights.
Okay.
Any more questions? Okay, if not, we thank Dr. Soman for his right and good presentation of and we move to next. Thank you so much. We move to this Niranjan Chaudhary for his his talk on statistical inference for subgraph frequencies of exchangeable hybrid model. Welcome, Dr. Nilanjan, and you can present your talk.
You are muted.
Yeah, you can.
Okay. Can you guys see my screen now?
Yeah,
Yes.
Okay, thanks. All right. So thanks, Dr. Satish Kumar, for the invitation pres- for presenting here. So the title of my talk is Statistical Inference for Subgraph Frequencies. I'll just go ahead and do it on the screen. Sorry. One second. I'm actually should be good. Okay, so the title of my talk is Statistical Inference for Subgraph Frequencies of Exchangeable Hyperedge Models. So this is a joint work with Ayushman Bhattacharya and Professor Robert Lundy at Washington University in St. Louis. So I will very briefly start with describing what a network is. The term network refers to a specific representation of what we understand as a complex data. Network data arises in multiple disciplines like political science, sociology, biology. Networks are mostly used to model or study the relationship or or interaction among various units or individuals. Traditionally, network analysis often reduces interactions to binary adjacency matrices, ignoring higher order interactions. Now, many datasets are collected by sampling interactions rather than nodes themselves. And in the context of statistical network literature, a hypergraph generalizes the concept of traditional graph. I'll go into it in my next slides. So unlike a simple graph where edges connect exactly two vertices, a hypergraph consists of hyperedges that can connect any number of vertices. So instead of just picking up the interaction, we collect the set of nodes and then try to express our graph. So if we try to do it that way, what comes out is a hypergraph. Okay, so this allows us to be more flexible and also makes it more natural to model certain different kinds of situations. So here are some examples of real life hypergraphs. So one example can be a collaboration network, where in a collaboration network, mostly if we are doing a traditional graph analysis for a collaboration network, what it typically lists is if the two people have collaborated or not. So if the two has written an article, they will say one. If not, then it's zero. But there are also other things. In a collaboration network of 5 people, there can be like different combinations in which people are writing papers or how many times they are collaborating. So all those information gets suppressed if we do a traditional graph analysis, but they become more pronounced when we are doing a hypergraph analysis. Similar examples can be framed from our shopping list transactions or social media hashtags. From Twitter data, we can do hypergraphs. I will not go into all the details now for the interest of time, but let me quickly try to show like what happens in when we try to do a binary network modeling. So the figures on the left is the list of the authors that are participating in collaborations. So the first one is saying authors 1 through 4 has collaborated in a paper. Then the next one is saying author 2, 4, and 6 have collaborated in a paper. Now, if you look at the matrix representation, so black means there is an interaction and white means no interaction. So you see just 1 and 2, there is like a black mark. That means they have interacted. 2 and 4 has interacted on the first paper and the second paper as well, right? And 2 and 6 has also interacted in the second paper and the fourth paper. But all those information are not reflected through a binary network. It only says whether they have interacted or not. Okay. So one way to incorporate the frequency of the collaboration is to do a weighted analysis. So if we are doing a weighted analysis, there you will see that the 2 on the matrix size is basically saying that these people have collaborated twice, right? But the information that's missing is on which papers have they collaborated. That will give us an idea about the research interest about a particular group or even one particular collaborator. That information is missing. Now, to even have that information, we need to model it through a hypergraph. Now, in a hypergraph, the data typically comes in the form of a list. Okay, so all these lists on the rightmost panel. So that's how we record the data. And then when we plot the data, that's the figure 6. And this is how it looks like. Okay, and it cannot be reduced to any form if we want to keep all the aspects of it. So that's the main difference between representing something in a graph or network or hypergraph. So there are some existing works that has been done in hypergraphs. So one of the main areas is the community detection part that has been done. And some models has also been proposed, like hypergraph stochastic block model has been a popular model. And then there are also some models that has been formulated based on the latent spaces. So these two are pretty popular examples, like Yu and Zhu and the Turnbull paper. Now, for today's talk, I'm going to talk about a class of subgraph frequencies for hypergraphs. I'll get into it in a second, what I mean by subgraph frequencies. And we discuss about some non-parametric asymptotic theory there, and also the concept of degree filtered subgraph frequencies, and a little bit of an application in real life collaboration network data. Okay. So a brief introduction about the subgraphs. So subgraphs are arguably the most important class of network statistics. In certain applications, a particular subgraph can be interpreted as a functional subunit within a larger system. For social networks, for example, a triangle count captures the frequency of mutual friendships. So this is an example where subgraph can be useful. I also gave an example earlier that for a collaboration network, the subgraphs can be uh, mm, subgraphs can carry specific meanings and it would be of specific interest. Interest in the inference on the subgraph frequencies started with the work of Bickel, Chen, Levina for sparse graphons. There they started studying and obtained the asymptotic distribution. Then further works has been done In among these papers, Lundy and Sarkar, they studied the subsampling phenomenon to do statistical inference. Green and Shalizi did some bootstrap to do statistical inference. Okay. Now for an exchangeable hypergraph model, I would say like how a subgraph count looks like. So the vertex set would be denoted by V, which denotes the countable collection of vertices. And then this is basically the framework that is talking about the probability space. And then the hyper edges, HIs, they are considered to be exchangeable. For simplicity, we can think that, you know, H1, H2, HM, they are IIT. So the hyper edges follow IIT with some distribution P. We are not specifying the distribution P because we want to leave it as a non-parametric framework. Now, based on this, we can obtain an expression of the subgraph. Now, that would be of the form of T of HC in the equation 2.1, which is where M is the number of hyperedges and R is the order of the subgraph. So if it's a triangle, then the order is 3. If it's something with 4, like a quadrilateral, then that would be R would be equal to 4. So that's the role of M and R in this formula. C, the formula of C is a bit more involved. So I will just say like C is a class of indicator function which just combines the hypergraph with the order of the graph. Okay. Now here actually, so for when you are analyzing binary network data, the subgraph frequency is a little bit more simple in the sense we do not have these many variations that we will see in a hypergraph. Because for example, in a hypergraph, there can be different kinds of triangles. They can be colored triangles or colorless triangles. So this subgraph frequency definition that I'm giving here is the one for colored, where we are preserving each and every individual aspects that is coming out of the hyperedge. Okay. And then the parameter, corresponding parameter is defined as the expected value of this. So if I go into the example in the next slide, then this will be more clear. So the equation 2.1 that I showed earlier, for a colored type 1 triangle, this would be like this. Now, what is this type 1 triangle actually telling us? It's saying that the three authors, the three nodes, which are the three authors, they have collaborated, but they have collaborated only in one paper. Here, the color of the edge denotes the paper. Okay, so by looking at this figure, I will say this is a collaboration that has happened in one paper. So all the three authors have collaborated in one single paper. Then the next one, this is the example of a type 2 triangle. Now for the type 2 triangle, this is saying that the authors, this and the two authors have collaborated in the red paper, and the third one has collaborated in the blue paper. Okay. Now for the next one, this is a type 3 triangle. This is saying that the three authors have collaborated. They have collaborated on 3 different papers, the red, blue, and the black one. Okay. So that's how it's keeping the information. So the colored triangles essentially preserves the identity of the edges. Okay. Similar to colored subgraphs, we can also define something like a colorless subgraph. This would be the expression of the colorless subgraphs. It looks a bit more involved than the colored one. Instead of explaining this, I would rather go into another example. So for colorless subgraphs, essentially what happens is it ignores the edge levels, but preserves the multiplicity. It do account for how many collaborations is happening. It counts those, but maybe not paper by paper. It does not preserve the paper by paper information, but keeps the total number of collaboration information. Okay. Now, this is an example of like, you know, how colorless triangles can show up. These three are the 3 examples of 3 paper. In the first one, authors 1 to 3 has collaborated. In the next one, 1 to 4 has collaborated. And in the third one, 2, 3, 5 has collaborated. Okay. Now, from this information, if you try to draw the hypergraph, this would look like this. Okay. Now, to find out colorless triangle, you first go and find out the color triangles. So essentially breaking it down into type 1 triangles, then type 2 triangles, and type 3 triangles. Okay. Now, type 1, type 2, and type 3 essentially are colored triangles. Now, if I add them up, so that way I add all the triangles, so all the information gets in, but I throw away the individual informations. So finally what I get will not have either a type 2 or a type 3 or a type 2 or a type 3 individually. It will have a collection of all of them together. So that is essentially how a colorless triangle is formed. Like, so here, if you see here, there are 3 type 1 triangles, and then here there is a 4 type 2 triangles, and here there is 1 type 1 triangle. So essentially, I would just multiply the frequency. I see a typo here for type 2, that should have been 4. So it's 3 times the type 1 plus 4 times the type 2 plus the type 3. That essentially gives us, if we do it this way, then the thing on the left hand side will give us a colorless triangle frequency. So colorless essentially preserves the frequency, but does not worry too much about preserving the identity of the individual hyperedges. Okay, so that's one way of formulating a colorless. There can be another way of formulating the colorless, which is the same thing. It's just scaled by a factor of m choose 3. That essentially will help us to do the asymptotics. Okay, now I'll quickly start describing the asymptotic framework. So now for this framework, for the ease of presentation, I would not say that we are doing for each individual hypergraph. Instead, each individual subgraph, instead we have collated them into one whole vector so that we get a multivariate CLT kind of a thing. And so this is THC1 and THCP. These are P many subgraphs. And so correspondingly, the parameter vector would look like P many expected values of it. And so this is the asymptotic normality result. So the first condition, 2.6, is essentially a variance condition type thing. So this is saying if the variance exists, then what we get is square root m times tc minus theta c, that goes into a normal distribution with mean 0 and sigma c. And then for a colorless subgraph, also we get similar central limit theorem type guarantees. Next, I will say like how we can have another definition of subgraphs, which is called degree filtered subgraph. Now, degree filtered subgraph is has a very nice practical motivation, in the sense when data for hypergraphs or graphs are getting collected, a lot of missing information happens. Okay, so maybe they threshold the data, so they do not keep all the information that's there for the nodes, and then people try to form these subgraphs. So essentially that would be a degree filtered subgraph. Okay, so most studies of robustness to node for these have happened when the nodes are deleted at random. And in the investigation that has been done so far is often limited to simulation studies. So it would be of substantial interest of how many such low degree nodes can be removed without affecting the estimation and inference. So the question at the end of the day would be, can the degree filtered subgraph recover similar type of asymptotic normality results that we just had before? Okay, so this is an example of a degree filtered hypergraph. And now in the, so the figure 13 is the hypergraph and the figure 14 is the degree filtered hypergraph. So what is happening, if you carefully look at figure 13, and the nodes that had 1 degree, so that means only one edge were coming out of it, they have been filtered out. Okay, so in the resulting degree 4, the nodes that had at least 2 different colors coming out of them, they have been saved. The others one has been zeroed out. So for example, the easy one to look at is 7, 8, 9. It only had 1 color. So when we degree filtered with d equal to 1, that was not there. In the degree filtered hypergraph, 7, 8, 9 does not have any edge. Okay, one interesting application or motivation can be, Suppose you are looking at a collaboration network, it's a movie collaboration. So if you go to the IMDb website and take down the cast information from the different movies, typically they list like 10 to 15 important cast in a particular movie. So the actors or actresses who have not appeared in many of the movies, their information typically tends to get filtered out. So that's called a low degree filtering. People who have not appeared more, their information does not seem too relevant to people who are sharing or storing the information. So they typically tend to leave those things out. So that's how we naturally get a degree filtered subgraph. Okay. Now, for a degree filtered subgraph, the first thing, most important thing here is to define how do we define a degree in a hypergraph. So this is how a degree hypergraph degree is getting defined. That a node J's hyperdegree is defined as indicator HI contains in J. So how many nodes are getting contained in the hyperedge? Okay, so that's how the hyperdegree is defined. Now, hyperdegree measures how many hyperedges a node participates in, which is a standard generalization of the notion of degree to the hypergraphs. Now, if we have this definition of hyperdegree, then we can modify our subgraph definition that I had in equation 2.1 to this, which is equation 2.7. Okay. Now, under that, we have this result that the subgraph minus the degree filtered subgraph under the same square root m scaling, this converges in to zero in probability. So essentially, after that, we will have the asymptotic normality result. Okay, so this is essentially saying that the behavior of the subgraph, original subgraph, and the degree filtered subgraph are not too different if we have the degree filtering, which is much, much less than m. Okay, so there I have just I'm just presenting this the most simplest case of this result. There are different orders of D through which we can see, and also there is a result which is showing like when this result will break. So at what degree filtering rate this hypergraph, degree filtered subgraph and the original subgraph, they would be different. Okay. The next thing that I want to show is, so for all these previous asymptotic normality results that I showed, they have this form of the variance, which is the sigma square, or previously I had the sigma c. Now, all these are asymptotic variances that are unknown in practice. Now, to do statistical inference, we need to have we need to estimate this asymptotic variance. For that, we have used subsampling. Okay, so this is a very standard subsampling procedure that will allow us to just estimate the
Dr.
asymptotic variance.
Nilanjan, you have 5 more minutes.
Okay, okay, thank you. I'll finish. Okay, so then I'll quickly go into the real data analysis. I think that is more interesting than the simulations here. So to construct the co-authorship network, we analyzed a collaboration network. So essentially, in the collaboration network, we had three journals and one movie collaboration. So the three journals that we had were two of them were statistics journals. One is JASA and the other one is JCTS. And the other journal that we had was from epidemiology. All these three journals are published by Taylor and Francis. And then we had another movie collaboration network where all the cast information was kept for 10 years from 2015 to 2024. Now, when we analyzed the data, uh, this is how the confidence intervals came out. Okay, so we have so this type 2 star type 2 clustering coefficient, these are the ones that are coming out of the hypergraph. So these are subgraphs coming out of the hypergraph. And then the binarized 2 star and the binarized clustering coefficients. So these are the subgraphs that are coming out of the traditional hypergraph. And we see that for a majority of the cases, the one that came out of the hypergraph could distinguish. So the ones in red means the ones that they found that the difference is significant. So the most interesting thing is if you look between JASA and JCGS, which is the comparison between two different collaborations in the same domain, there the type 2 clustering coefficient could figure out the significant difference, but the binarized clustering coefficient failed. So that is given an indication that a hypergraph based analysis can have leverage the extra information that I said that can be retrieved, and then using that we can do meaningful inference. Okay, so I'll quickly do a summary. So in this work, we had the non-parametric framework for analyzing hypergraphs, and we had theoretical guarantees for colored and degree filtering cases. And we also had the generalized subsampling estimator that helped us to do the statistical inference. So these are some of the standard references that I used. And thank you. This is the link to our paper. So if you guys are interested, you can take a look. Well, I'll stop here. Thank you.
Thank you, Nilanjan. Now it's time for question and discussion. If anybody has any question, they can ask now. Yeah, please, sir, ask.
Sir, see, this is when you add more information, the dimension gets increased. Say in your first example, when you are not going to the account for frequency, it is simple. When you account with color or some other dimension, you are going for a higher dimension. Can it not be accommodated with the classical multivariate setup in which the coordinates points are combination of authors, something of that sort? That is one thing. That is what I try to convey is that as we increase the information or dimension, okay, so something like a vector itself, more with more components, then we can deal. So in this approach, do you have any advantage over dealing in the classical way in which vector dimension is increased?
Okay, that's a good question, actually. So I would say essentially when we are recording the hypergraph, after that, when we analyze the subgraphs, those are univariate quantities. So each triangle that I showed, that's a univariate scalar quantity. Okay, so essentially the dimension is not getting increased there. But if we analyze like maybe thousands of subgraphs together, then we can have like a high dimensional problem. But here, after collecting the information, when we are analyzing the quantity of interest of the statistic that we have, that's still a univariate statistic. So the dimension or the increasing dimension is not directly causing an issue over there. I don't know if this answers the question, but
Yes, to some extent, but that gain comes from some limited structure, it seems. When we have more combinations and more numbers present, then identifying the or reducing the dimension in terms of less dimensional graph, okay, so that is going to take much time or something of that sort. That's what I am trying to
yes,
see.
I would say then traditional graph analysis, computation of subgraphs from a hypergraph will take a little bit more time. So that's why all these are essentially a class of use statistics, but we have to do some sort of a incomplete use statistics type analysis to reduce that computational time. But on the other hand, what I showed is one of the gains are where the tradition, because a hypergraph has more information. So if we carefully choose a statistic based on the hypergraph that can leverage that information and maybe find out significant differences that a traditional graph may omit. So that can be one of the potential advantages of incorporating this complicated structure. Thank you.
So one more. So we can use this for the longitudinal data.
Yes, we can also do it for longitudinal longitudinal data kind of represent.
Pleasure to introduce our session chair, Professor Venkatesan from ICSMR. Professor Venkatesan is a distinguished academician and researcher who has made valuable contributions to the field of statistics through his teaching, research, and academic leadership. We are honored to have Professor Venkatesan chair this plenary session. It's now my pleasure to introduce our first speaker, Professor Jaya M. Sathagoban, Professor and Associate Dean for Faculty Affairs at the Rutgers School of Public Health, Rutgers University, New Jersey, USA. Professor Sadhagoban is an internationally renowned biostatistician whose research focuses on cancer epidemiology, statistical genetics, and public health. She has made significant contributions to cancer research and biostatistics through her extensive research, publications, and academic leadership. Our second speaker is Professor Gauri S. Datta, Professor of Statistics at the University of Georgia, USA. Professor Datta is an internationally recognized statistician whose research interest includes Bayesian analysis, survey sampling, and small area estimation. His pioneering contributions have greatly influenced modern statistical research and applications. Now I respectfully invite Professor Venkatesan to kindly chair the session and commence the proceedings. Over to you, sir.
Thank you, Professor Parvati, for giving an introduction. So, Professor Sadish, so good evening. So, I think, first of all, thank you for inviting me to chair the session. There are two eminent speakers in this one. One is Professor Jaya Sadagopan, we know very well because he is alumni of Madras University, so we know we are very proud because I am also from the Madras University. There is one connection. And we know we had talked a lot of things. And already the speaker has been introduced. To add one more thing, so Professor Jaya has got more than 30,000 citations, which is a very, very rare thing in our statistic thing. And our H index is about 67 or something like that. So academic output is so high valued. And with this brief introduction, may I invite Professor Jaya Sadagopan to talk. So total, the session is going to be about two speakers. It is allotted about 80 minutes. That means each one will have 40 minutes. So I request Professor Jaya to talk about 30 or 35 minutes, so the next 5 minutes will be for discussion. With this, without wasting time, now may I request Professor Jaya to give a talk.
Thank you, Professor Venkatesan and
Yeah.
Professor Parvati, and thank you very much, Satish, for organizing this and for having me here. Before I begin, I want to say that this morning, we woke up this morning with a huge thunderstorm. We lost electric power. So I have a generator outside that's helping me power this computer and my internet. If my generator dies, I will disappear. So if I disappear,
Yeah.
please move on to the next speaker. I will figure out
Oh,
something.
even US we are having the problem. Huh?
Oh, it's a big problem. Yes. Okay, let me share my screen. Okay. I hope everyone is able to see my screen.
Yeah.
Okay, so before I begin my talk, I want to pay my homage to Professor Yegin Thomas, who we lost recently. Although I did not have the privilege of personally interacting with Professor Thomas, I understand the impact he has left on the university and in our profession. So I want to say, may his life and his works continue to inspire us to use statistics and data for the betterment of our society. And I also want to share a very happy July 4th with everyone. It's just any other day for everybody in the world. And here in the United States, it happens to be the Independence Day. I showed two pictures of the fireworks from last year's Independence Day celebration. I don't know what's the status this year with the storm. But with that, I want to move on to the today's talk, where I'll talk to you about, I'll share with you some results about an ongoing study. Very simple results in the sense, just a couple of results from among an array of results that we have. And this is a joint work with several students. And I want to especially point out to Tina Dharamdasani, who worked on this study towards her PhD and just completed her PhD and got her degree 2 months ago. And also several colleagues. And I also want to highlight the cancer registry in New Jersey with whom we collaborate on this study. So breast cancer is the most common cancer among women around the world. And I show two pictures here. On the left side is a picture with a bar graph. This is from the Global Cancer Atlas. And it shows the incidence rate of different cancers. We can see breast cancer is way at the top. There are several other cancers too, but a very distant second, definitely compared to breast cancer. And on the right-hand side, I show a map of the world. So I asked the Global Cancer Atlas, show me the most common cancer for women around the world. The most common cancer happens to be breast cancer around the world in every country. And it's shown in pink here, but the intensity of pink is different. A very deep reddish color indicates that there's a very high incidence rate in these countries, and a very low pink or almost violet or closer to tending to whitish color indicates very low incidence rate in these countries. Nonetheless, breast cancer is the top cancer in every country shown here in this world map. So clearly something needs to be done, and some things are being done. We have made several advances in cancer. But still, more needs to be done. We cannot just say enough and move on. Especially when we look at women from South Asia. South Asia is largely India and also encompasses Pakistan, Bangladesh, Nepal, Sri Lanka, Bhutan, and the Maldives. And there are two figures here. The left-hand side figure shows the incidence of breast cancer in the United States, which is way at the top here, and the incidence of breast cancer in South Asian women, and going all the way from 1990 on the x-axis up to 2022, for which I was able to access data. And these are data from the IMHE website. And what each point shows is, for a particular year, the number of new breast cancer cases per 100,000 women. So for example, in the United States, if we look at every 100,000 women, about 200 plus women are identified as having breast cancer that particular year, diagnosed that year. While in South Asia, we have out of 100,000 women, or 1 lakh women rather, about less than 50 are reported as having diagnosed with breast cancer. So clearly, South Asia, the breast cancer incidence is very low compared to the United States. But whereas, while the incidence has definitely been dropping a little bit in the United States, the incidence is going up in South Asia. And on the right-hand side, I show incidence rate of breast cancer in the United States. The black lines are incidence rate of breast cancer for non-Hispanic white women, or maybe Caucasian women, if we can say so. And the red lines are breast cancer incidence rate for South Asian women living in the United States, like women like me. So we call them South Asian American women to distinguish them from South Asian women living in South Asia. So the bold lines, the black bold line and the red bold line, show the incidence rates for non-Hispanic white women and South Asian women respectively. So non-Hispanic white women definitely have a higher breast cancer incidence rate than South Asian women. And this only goes up to 2014, because at 2014, we do not have the ability to identify who is South Asian in the incidence rate database of the cancer registry here. So that's an issue, that identification of the race ethnicity of the people, especially of South Asian subgroups like Asian, Indian, Pakistani, and so on, stops at 2014 for the incidence database. And we can see that the incidence rate has been increasing. And there are two dashed lines. While the bold line is for the entire United States, the dashed lines are for New Jersey. So the incidence rates for non-Hispanic white women in New Jersey and for South Asian American women in New Jersey mirrors what we see also in the broader United States. So clearly this says that yes, breast cancer incidence rate, although it is declining a bit in non-Hispanic white women, more immigrant populations like South Asians, they are seeing an incidence, increasing incidence rate, and in fact, a rapidly increasing incidence rate here. And we see such a trend also if we plot Chinese women, Japanese women, Vietnamese women, and so on. So together it says something needs to be done about the breast cancer incidence or how to manage breast cancer in these women. And one of the issues for understanding why breast cancer is increasing, what kind of breast cancers these women have, especially immigrant populations and so on, is quite challenging because we do not have much data about the health of these women. So the data, especially of South Asian women, are very, very scarce. And to give an example, I show here the sample size of different populations, including South Asian, Asians rather. This comes, somebody is talking. I'm wondering if we can mute. Thank you. So this is coming from the National Cancer Institute's like a repository called the Cancer Epidemiology Descriptive Cohort Database. And we can see in this database, they have a lot of data coming from different populations. The white, non-Hispanic white women, there are more than 70,000 women, and it quickly plummets. More than 6,000 for Black, around 2,000 something for Hispanic women. And for Asian women, it's all the Asians combined, Filipino, Chinese, Vietnamese, Indian, Pakistani, everybody combined. And that distinction, who is from which specific part of Asia, is not available, but they are only like 3,500. So South Asians will be a subset of this 3,500. So clearly there is very limited data, and when there is no data, you are not seen typically. And so it's very hard to understand breast cancer in these populations, especially South Asian women. So to understand breast cancer better in South Asian women in the United States, I decided to wear, I am a statistician. That's how I'm trained. That's who I am. So I wore a little bit of a different hat, collaborating with my colleagues to engage in primary data collection to understand breast cancer in South Asian women by navigating this gap. So we established the study called Cancer Analytics on South Asian Health, Breast Cancer, or Cancer BC study. At the outset, what we did was we explored data from the breast cancer, from the cancer registry in the United States, the SEER Cancer Registry. And we investigated what are the characteristics of breast cancer in South Asian American women that are available in this registry, right? So since cancer is a notifiable disease in the United States, every woman that is diagnosed with cancer in the United States is available in the registry. So South Asian women are also available in the registry, that is South Asian women living in the United States. So our work, which we published in 2021, this QR code will take you to the link. What we found in this work, studying South Asian women versus non-Hispanic white women, is that South Asian women are younger at the time of diagnosis compared to non-Hispanic white women. For example, a non-Hispanic white woman's average age at diagnosis will be 62 years, whereas an average age at diagnosis of South Asian women living in this country is 52 years, a whole 10 years younger. And we also found that South Asian women, when they are diagnosed with breast cancer, they present with more advanced stage disease, that is more distant stage or regional disease, as opposed to localized stage disease, for example, higher grade and so on, at the time of diagnosis. So clearly they have some kind of like a more aggressive-ish form of cancer, and we want to study why this is happening. And so we established our Cancer Analytics and South Asian Health Breast Cancer Study as a companion to another study that is happening here in Rutgers University called the New Jersey Breast Cancer Study. It is a study led by my epidemiology colleague, Dr. Elisa Bandera, and she's studying breast cancer in Black and Hispanic women. So we said, I will run the South Asian study as a companion to this so that we have a multi-ethnic cohort study of breast cancer. So what is the goal of the Cancer BC study? Our goal is to investigate risk factors associated with aggressive form of breast cancer in South Asian American women, and also to study the quality of life after the diagnosis of breast cancer, and to identify are there unique risk factors that South Asian women have, or are the risk factor in us the same as the risk factors found in non-Hispanic white women or other populations. Because those investigations will allow us to understand are any unique aspects of breast cancer management needed for these women. So we designed the Cancer BC study to be a population-based study, and we collected data on lifestyle factors, reproductive history, medical history, treatment history, family history, and so on, using an extensive validated survey or questionnaire. And we also collected saliva samples for conducting future genetic studies, because all said and done, cancer is a disease of the genome. So many environmental and lifestyle factors will affect that. And ultimately, studying the genome is also important in addition to studying all these other characteristics we collect from questionnaire. And one of the challenges of studying the health of South Asian women is, at least in the United States, there is very limited data and women tend to not participate. It's very hard to engage these unique populations in scientific research. These people may themselves be researchers doing study, but to participate in a study is very limited. So we wanted to know, yes, we want to do this study and collect data, but is it even feasible? So we established a feasibility phase or the pilot phase. And we said, as a feasibility, we will see, can we collect data from at least 100 women or up to 105 women? 100 to 105. We want 100 women, but up to 105 to give a buffer in case somebody is unable to complete the study and so on. And we said, can we collect saliva from at least 65% of these women? These are based on successes found in other studies. And the eligibility will be anybody that is female of age 20 and above is when breast cancer is commonly diagnosed, not in women less than 20 years. And we also wanted women to be diagnosed in New Jersey, and we wanted to recruit women who were diagnosed very recently. But at the time of initiating the study in 2020, recent year was 2021, and we were going back 1 year at a time as we start recruiting women from recent years. And women should be able to speak English or a South Asian language. Common languages spoken in this country among South Asian families include Gujarati in New Jersey and Hindi in New Jersey as well. And they must not be living in a nursing home so that they will be able to engage in this study. Because nursing home cases have a different characteristics that need to be studied separately. So there are two figures here that tells us our recruitment. So I will not go through the gory details of all the things that I learned as a statistician collecting data. So what we did was work with the registry, and the registry identified initially 480 women they contacted out of many women available. And ultimately, we were able to collect data from 101 participants. And this is the rate at which our data collection increased. We started in 2022 December, and there was a gap where we had to wait for Ramadan and the Lent period and so on. And then it went, we continued collecting data. And this is a map of New Jersey. Where do our women come from? Women come from mostly from Middlesex County, which is where a large Indian population lives, Somerset County, and so on. And there are some counties where we have no women. There is very limited Asian population, especially South Asians living there. So we captured women from, in general, places where South Asians live in the United States, or in New Jersey rather. And what we also show here is a world map. The women that are a part of our study, not only, this is the country of birth of these women. So some women are from United States, so that's Alaska, and that's Hawaii. And several women are also born in India, Pakistan, and Sri Lanka. But interestingly, there are several women of South Asian origin in the United States who said they were born in East Africa, that is Uganda, Tanzania, Kenya. And there were women born in Libya, Ghana, and there is somewhere here or somewhere here. Hawaii must be somewhere here. So maybe somewhere here is Fiji. There are some women born in Fiji representing the South Asian diaspora. So we asked several questions. I will not go through every single assessment that we did. But one of the questions that we asked is the incidence of breast cancer in the relatives of these women, female relatives of these women. So we have 101 women with breast cancer. If we look at the female relatives of these women, are there breast cancers occurring in their relatives? That is seen more often than we would expect by chance. So cancer occurs in families. So if we look at the families of these women, are their family members, female family members, having more breast cancer than we would expect by chance? If the answer is yes, then it would be a very important indication of inherited genetic mutations, inherited genetic factors, or shared environmental factors that may contribute to breast cancer, and those need to be studied. And also understanding these will also allow us for better patient management, and also provide better preventive counseling for family members, and also improve overall public health, because we are engaging in prevention strategies. And also it improves risk stratification of patients, and we can identify who are at higher risk for breast cancer and who may be at lower risk for breast cancer. So how can we answer this question? What would be a statistical metric for answering question? How do we measure, is there higher familial aggregation of cancer in these women? The statistical metric for this is the standardized incidence ratio, or SIR, and that, coupled with Lorentz curve, provides us with some insights that we can use for risk understanding risk stratification. And what is the standardized incidence ratio? Here on the left, I show the image of a book by Breslow and They, a very important book. I have it on my desk all the time in my 30 years of my career. So what is standardized incidence ratio? It's a ratio, so it's as a numerator, relatives of these 100 women, known as the familial incidence rate, for example. And the denominator is the expected number of breast cancer. So observed divided by expected. What is the expected number? It is the number of breast cancer we would expect occurring in the population, or the population incidence rate. Is the familial incidence rate higher than the population incidence rates? That is the standardized incidence ratio greater than 1, or does its confidence interval exclude 1? For example, a 95% confidence interval. So if that happens, it is an indication that there is a very significantly high aggregation of breast cancer in families of these women. So the numerator we can get from our data. We have 101 women. Each woman we ask, does your mother have cancer, sister have cancer, aunt have cancer, daughter have cancer, and so on. And we capture how many family members, female family members are there, and how many women out of those number have cancer. So that we can capture from our data. The denominator is the incidence from the population. It's the population incidence rate. So what is our population? So we are capturing women diagnosed with breast cancer in New Jersey. So does that mean the population is just all the women living in New Jersey? But we are also capturing the family members of these women who are diagnosed with cancer in New Jersey. So the population is all the family members, and it turns out that majority of the family members are living back in South Asia, either in India, Pakistan, Sri Lanka, and so on. So using the population incidence rate in the United States is not a fair comparison, because the family members are actually living in India. So their incidence rate are in South Asia. So their incidence rate in the population should mirror the incidence rate of the South Asian population. So the denominator, we captured the expected number using the IHME online tool for capturing incidence rate in the population. So with that, I show you the data that we have. So we have 101 women in our study in different age groups. And I put this in different age groups because the incidence rate of cancer can be different according to the different age groups. Right? So, for example, there are 13 women who were diagnosed with breast cancer in our study under age 40. These are early onset diseases. And they reported totally 96 relatives, these 13 women, of which 4 relatives had breast cancer. And we can compare this with the population rate and calculate the standardized incidence ratio for that age group. And likewise, we did this calculation for each age group. Right? And what we found was that the standardized incidence ratio shown here in the green last row is SIR is 3.2. So that is familial rate is 3.2 times the population rate. There is a significantly high familial aggregation of breast cancer in our cohort of women, 101 women in our study. So there is familial aggregation of breast cancer, and this figure shows an additional thing. So there are 13 women under age 40, 41 women in age group 40 to 49, and so on. And this box plot shows these 13 women reported 96 family members, of which 4 had breast cancer. What is the age at diagnosis of breast cancer of these 4? So younger women tended to have younger family members, younger age at diagnosis in their family members, and it went up with age. And of course, there is a drop here, which we need to understand. Either this is not surprising, because at a higher age group, these women or their family members have probably died of other causes like cardiovascular disease and so on. So there is a dip here. But that needs to be scrutinized even more to get a better understanding. But what this says is there is a higher familial incidence, but SIR of 3.2, fine. SIR of 3.2 is SIR of 3.2. What can we say? Can it tell us how to project breast cancer burden? And that it can say by taking advantage of the relationship between SIR and Lorenz curve. So I just have like 2 or 3 slides, I guess. I will quickly go through that. So what does it mean by saying, can we summarize SIR in a way to help us project breast cancer burden in these women who currently are without breast cancer in the family members? So we can do that. In order to do that, let's think of it hypothetically as follows. Suppose we are able to assign risk to each family member. You say you have a 3% cancer risk. Another woman in the family, you have 75% risk. Another woman, you have 83% risk. Another woman, you have 27% risk, and so on. So each woman has some risk of breast cancer. And suppose we order these, all these women according to the risk, lowest risk to the highest risk. Can we take the look at the women who are given the highest risk, the highest 25% of risk? So it is only we are giving the risk. And if we follow up these women, how many of these women with very high risk will eventually indeed end up developing cancer? If women with very high risk indeed end up developing breast cancer, then we can say by risk stratification, we can very well identify women who are going to get breast cancer. So can SIR capture this information? And SIR can capture this information through the Lorenz curve. So how do we do this? So, for example, we have every woman, let's say, for example, is given a risk, some percentage or some value between 0 and 1, 0.03, 0.27, 0.75, and so on. And this risk has a distribution, right? Cumulative distribution. And in a relative, what is the distribution? What is the risk in this woman, given that her relative already has breast cancer? So if I am a woman in the study, that means I have breast cancer. What is the risk of my mother? What is the probability that she will develop breast cancer, given that I already have breast cancer? I am in this study. And the risk for my mother would therefore be a size bias distribution, and a lot has been written about it. Most common or important ones include the paper by Patil Rao and also the paper by Begg, with whom I had the privilege of working for several years on several of these topics. And based on the size bias distribution, we can write the probability density function of risk in my relative, that is my mother or my sibling and so on, using a size bias distribution. And also I can write the cumulative distribution of risk in my relatives. And one of the common distributions for risk is the log normal distribution. So for example, this f of r, logarithm of r, can be treated as a normal distribution because breast cancer is a rare disease in the population. So as a result, log normal distribution is not an incorrect distribution. And under the log normal distribution, we can write the cumulative distribution of risk in the population and the cumulative distribution of risk in family members. Okay? And these can be written using the normal distribution. But what is very important is to show that we can use these to draw the Lorenz curve. So the Lorenz curve is the percentile of risk in the population and the cumulative distribution of risk in the family member. It's a plot of this gives the Lorenz curve. And this one requires us to get the variance of the distribution of risk, or the standard deviation of the distribution of risk in the population. Right? So how do we get the standard deviation of the distribution of risk? That can be captured using the standardized incidence ratio. So in one of my early works with Dr. Colin Begg and others, we showed that the standardized incidence ratio is 1 plus the square of the coefficient of variation and risk, which is the coefficient of variation is the standard deviation divided by the mean. And we can use the standard deviation is sigma, and we can use this to capture the relationship between sigma and the standardized incidence ratio.
Sorry, Professor, just another 3 minutes, sir, that means.
Okay, I will be done in 1 minute. Yeah, thank you. Thanks very much for the reminder. And this plot shows that, so when a standard deviation is very high, essentially the tail distribution of the log normal is very high. So there is more and more women with very high risk. So large standardized incidence ratio is equivalent to larger variation or very heavy tail distribution. So there will be more and more women with very high risk when the standardized incidence ratio is very high. So in the case of our study, the standardized incidence ratio of 3.2 corresponds to a variance or a standard deviation of 1.08. That means if we assign risk to all these women, the relatives, one woman, my mom has, let's say, 3% risk, my sister has 72% risk, my daughter has 23% risk, and so on. And like that, if we do this to all the relatives of these 101 women in our study, we can rank the people according to their risk. And the women with the highest quartile, the highest 25% of the risk, women, 66% of the cancers will occur in the highest quartile of women who have been assigned this risk estimates. So that is what the standardized incidence ratio translates to. Essentially, it tells us what is the burden of a cancer we can expect in the highest quartile. And in this case, 66% of the cancers are expected to occur there. So that is the interpretation, and what it essentially says is it is useful for risk stratification, and it has very important implications for studying genetic and shared environmental risk factors. So uh, all we did was a study on like what is known as a population based study. But one of the aspects is when we as statisticians, when we get data, this is a population based cohort, we go ahead with the population based cohort with our work, with our design analysis and so on. But even in a population based study, the participation of the women need not be always random. So what we found was in our study, there are 53.5% of the women are under age 50 years, whereas in the registry, only 36.4% of the South Asian women are under age 50 years. So that says women are, there is some issue about choosing to participate in the study. Right? So that is what we are trying to now move forward with to understand this better. So our work is allowing us to understand familial aggregation, but we want to know, are women only with familial history of breast cancer willing to participate in the study? How are we going to capture this? This is typically not addressed in any population-based study that I have encountered so far. So we are currently pursuing the second phase of the study, where we are pursuing targeted recruitment of older women by engaging in survey data collection via not just English, Hindi, or Gujarati, but expanding to other South Asian languages as well. In fact, we just completed an interview in Telugu, and also one in Malayalam is coming up next week. And we are also asking women what motivated you to participate, so we can see how many of the women also respond saying it's because my family member had cancer, or any other reasons they provide. So overall, this has been a very eye-opening experience for me, and it continues to be. As a statistician, I work with data, I work on modeling, I work on methodologies, but this is an opportunity for me to engage as a primary in primary data collection as a statistician. And it's a key aspect of my own evolution as a statistician, from someone who works with other people's data to move on to primary data collection for filling the gap in lack of data in South Asian women. And very interestingly, this morning I read an editorial in the Hindu where they're talking about making cancer a notifiable disease, because they say at the heart of the issue remains lack of data on cancer in these women. So with that, I wrap up, and thank you for bearing with me. So happy to answer any questions you may have.
Thank you, Professor Jaya, for your wonderful presentation. I think very informative presentation. Now the paper is open for discussion. Any comments, suggestions, or queries, please be free to ask her. At least one or two questions per expert, because we got another 2 minutes time for Professor Sadish. You got any question?
Sir, shall I?
Yeah.
Madam, it's a wonderful presentation, connecting almost all abstract things to converge to a real point where we can make quantitative decisions and risk quantification. But my doubt is how we can justify the distribution of risk to follow normal. Is there any calculation done for that assumption?
Yeah, it is. There is a lot that has been written about it. I definitely encourage you to read the work of Farrow and colleagues. It is a paper published in 2002, I think. Yeah, I can find it. So essentially, the occurrence of cancer, if we think of it as a binary outcome, a woman has cancer or does not have cancer, right? So typically when we have risk factors and we want to see which ones are associated with the binary outcome of cancer occurrence, we would fit a logistic. It's a binomial distribution, and with some probability p, and we will fit a logistic model, right? Log of p over 1 minus p is some beta naught plus beta 1 x1 and so on. So essentially we take it's a Bernoulli outcome, right? Occurrence of cancer. So now if cancer is a rare disease, right? Breast cancer is a rare disease. There it is an increasing incidence, but if we look at the population size of few billion people versus the number of cancer cases, it's a rare disease. So what happens then is the denominator of log p over 1 minus p. The 1 minus p is approximately 1. So the logarithm of p is what we are modeling, as if we can approximate it as, right? And then we can take advantage of some relationship between those, the right-hand side and the normal distribution, or the model we write for log p and the normal distribution, and we can approximate that. So that is the idea that Farrow and colleagues have proposed.
Okay, I think any other one more question we can have? Madam, just I got one query. What is your definition of South Asian American or South Asian?
Yeah. So these are all women living in the United States with ancestry from South Asia, at least their grandparents.
What is the area of South Asia? Whether it's South Asia,
areas of
South
Asia. Yeah. So South Asia are the countries that I showed in one of the slides. Probably it comprises of India, Pakistan, Bangladesh, Nepal, Bhutan, Sri Lanka, and the Maldives.
Oh, because normally Southeast Asia means Afghanistan to Vietnam you used to consider. You are having this definition. Okay.
So that is the World Bank definition.
Yeah, that's
and
it. Because
World Bank
Southeast
does
Asia
not
means
include
Afghanistan to Vietnam, but you also, most of your the figure you showed all the samples you are taken only from Indian origin, most of them, 90%.
Yes,
right?
yes. So,
okay.
Yeah, because Vietnam, Philippines, and so on are considered Southeast Asia.
Yeah.
And Afghanistan is not included in South Asia in many of the registry work.
Okay. Thank you. Thank you, Professor, for your very nice presentation on behalf of the organizers and on my own behalf. I thank you for your taken all the time to see that you are presenting every year, all the conference we are seeing. Also, Sadish is seeing that you are coming regularly for this one. So thank you. Then I think now is the time to invite the next speaker, Professor Gauri Datta. Yeah, from this one, Florida, University of Florida, Gainesville. I think already he has been introduced by the person. But however, to add on, I think as far as academic things are concerned, he got more than 3,000 citations to his credit, and his index is about 32 or 35, something like that. And one of the well-versed professors over then, I think from the Malay group, we are having another gentleman. So from this one, now I call upon Professor Gauri Datta to make his presentation. Your time is about 35 minutes. 5 minutes we'll have a discussion. Please, over to you, Professor.
Well, thank you. Good evening. Here it's morning, like 10:15. Your place like almost 7:50. Thank you. Okay, let me see if I can share my screen. Okay, if I share the entire screen, that will work. I don't know. Window. No, let's see.
It's not coming. I think.
I know. I'm
just.
Yeah. Let me see if I can.
Yeah.
Chrome tab. Select a tab. Okay. If I select a tab. I want to select the window, okay?
Yeah, it's not, slides are not visible.
Probably. No, it is not visible. I can see that thing. I'm still trying.
I think You can send it to Professor Satish Kumar, where from there they can operate the slides also.
Yeah,
before
maybe if you can,
Yeah.
share next
I think
week.
you can send it to Professor Satish. So from there, people will be operating once you are asking to
Yeah,
make this.
hopefully I can also see the screen. Okay.
You can see.
Okay,
You
good,
can
good.
see. Yes, you can
That's
see.
why I sent it to the Shratish, beforehand. Okay, all right, thank you. Yeah, while you are setting it up, I'd like to let you know that I graduated from University of Florida, Gainesville, but right now I am a professor in University of Georgia.
Professor Satish Kumar. So, what is your thing? So, we are asking Professor
So
to send the slides.
whether we can share it from here.
Send the slides to you or anybody from Parvati so that they can display.
Hello, sir.
Dr. Parvati, you got the slides?
Sir?
Yeah,
Yeah,
okay.
yeah,
It is
yeah.
visible. It is visible, yeah. I think you can proceed, Professor.
Yeah, can it be,
The
like,
slides we can able to see.
yeah, I think this
Okay,
is good.
fine.
Now it's fine.
Okay, thank you very much for your patience and for helping me out. I hope everybody can hear me.
Yeah.
This is a joint work with some of my collaborators, Professor Ungsu Chatterjee, one of our former students, Iren Hu, my colleague, Dr. Buday Mandal, and my another colleague, Dr. Jerry Maples. So how do I go to the next slide? Okay, please go to the next slide. So this talk is, mostly focused on small area estimation. However, some of the ideas can be also applied to other context. Okay, particularly this ranking. Ranking is not necessarily restricted to small area estimation. You can rank it many populations using this method. So can I have the next slide, please? Yeah, so this is basically a brief introduction. So I will go through some of these items here. So please go to the next slide. Okay, so yeah, here we have like a map of USA. Basically, it is from the its income for different states. Like we have here 49 contiguous states and Washington D.C. in US. This number coming from 2000 census. So basically, you can see that different states have different median income. Okay, these can be considered like the true thing, true values, and based on these things, you can basically rank these states in terms of their incomes. However, you do not have the census every year, but you really like to see update of those values. What's the income, or what's the which are the poorest states in the country, like that. And for that, you are going to collect data through surveys, and that survey sample size is often not large. So the corresponding estimates are kind of less accurate. So in the smaller estimation, we try to use some sort of modeling and covariates available, auxiliary variables. Suitable modeling, maybe like linear models, mixed linear models, or generalized linear models, like that. And it's basically um, an appropriate extension of Stein's shrinkage estimation. So that's basically the smaller estimation. So we are going to talk about point estimation, measure of uncertainty, posterior variance, and things like that. Mostly we'll focus on the ranking, the Bayesian approach to ranking. So could we please move to the next slide? Okay, thank you. So, as I said, that this idea here, the key idea can be applied outside small area estimation, but we will mostly focus on small area estimation. We'll start with the available frequentist solution for ranking of several states and then we will present a Bayesian alternative to that problem. So could you please go to the next slide? Thank you. So main points basically, I have two goals here, but I'm not sure if I'll have the time to go to the next concept. So mostly I'll focus on ranking of several entities, okay, which is like, as I said, the states or small areas, or it could be various players, like, or maybe soccer teams. Right now, World Cup is going on, you can use data, and based on the data you can come up with ranking. Okay, so this is the thing we will talk about in the context of smaller estimation. Ranking is important. Many government agencies like here in India, we produce estimates of various quantities like income, unemployment, or certain disease, the cancer incidence rates that the previous speaker presented. And you might want to rank the most vulnerable communities, okay, in terms of certain characteristics. And that's the approach we are going to talk about. There are some examples here. And the other, could you please go to the next slide? And the other thing is that this is specifically for the small area estimation, which is basically benchmarking. So what is the small area estimation is based on statistical models. And from the models, you get estimates for various states. However, you can also get estimates of those states directly from the survey data. And when you combine all those estimates for the whole country, the sample size is kind of reasonably large enough to justify the accuracy of the estimate at the national level. Okay, so you want to make sure that your estimates that you get from the modeling for the individual estimates, they must also agree to those national level average. Okay, this is called the benchmarking or agreement. This is important for the national policy because you know that statistical offices, they don't want to publish several estimates when they are not um, agreeing with each other. So it is kind of a political necessity as well. So we are going to talk about, hopefully I have time to discuss that, but anyway, please go ahead. Next slide, thank you. So, I have listed here, list of topics on small area estimation and different approaches. These are mostly talking about point estimation and estimation of uncertainty, like that root mean squared error or coefficient of variation or posterior variance, like that. So anyway, so please go to the next slide. So we are going to focus on the identifying the areas or individuals or entities which could be yielding the largest or the smallest mean value based on the estimate. And the goal is accurately estimating ranks of uh, several or all the small areas. And in that context, I'll start with this frequentist paper by Klein, Wright, and Wieczorek in 2020 JRSSC. They basically proposed a frequentist method of uh, constructing joint confidence set of the rank vector of the M subpopulations. So could you please go to the next slide? Um, so what is why ranking is important? As I told you that various government offices or agencies, statistical offices, they provide estimates, on some characteristics for various states or provinces like that. And people usually look at the point estimate Typically, with the point estimate, we also publish the associated standard error. Okay, but people usually ignore that standard error column. They basically try to rank, mentally from the point estimates, and then they will say, "Oh, the Kerala has the highest literacy rate, and some other state has the lowest literacy rate." But maybe next to Kerala, maybe some other state very close, but due to sampling fluctuation, it might be maybe the other state might be a bit ahead. So you need to really account for this uncertainty in your rank point estimated, and that was the thing. This paper by Klein, Wright, and Wieczorek, they discussed about it. Could you please go to the next slide? So here, basically you cannot read that thing. It's a couple of the table from that paper, GRSSC 2020. You see that the commuting time in different states of US for the workers, and we have the point estimate and associated margin of standard error. Those numbers came from the American Community Survey. There are errors there. So based on that, they created some kind of ranking. Could you please go to the next slide? And okay, further down. Okay, so there are some literature review, mostly the Bayesian, initially we have the frequentist approach, and then subsequently we have the Bayesian thing. These contributions mostly talking about inference on individual ranks. Okay, we like to talk about joint rank, inference on the joint rank, the entire rank vector or subset of the rank vector. So could you please go to the next slide? So next slide. So some notation. So basically what we have, the theta 1 to theta m, the true means based on which we want to get the rank, and the rank vectors basically R1 check to Rm check. Those are the true ranks based on the thetas, but we do not know the thetas. We basically estimate the thetas through some measurements, maybe survey or maybe just statistical experiments. So we have these point estimates Y1, Y2, Ym, usually unbiased. And so based on these numbers, we can also estimate the rank, true ranks, and they're like R, capital R1 to capital Rm. And then I said that since Y1, Y2, Ym, they might change from sample to sample, that will result in change in the estimated ranks capital R1 to capital Rm. So it's not appropriate for a set of survey estimates to report these capital R1 to capital Rm by ignoring their associated error, okay, standard deviation or something like that. So could you please go to the next slide? Yeah, so this paper, they assume this normality of the population. I mean, the sample mean, estimating theta I. And then in doing this thing, how to create the rank, basically they constructed joint confidence sets by simple application of individual confidence interval for each of theta 1, theta 2, theta m. And then basically they calibrated each of these intervals such a way that joint confidence intervals given by this Cartesian product of these m intervals, so that the overall coverage, that confidence set, I call it Cartesian product, will be having probability 1 minus alpha. Now, once we have these things, then we can use these intervals to construct the various possibilities of rank allocations. Okay, so could you please go to the next slide? So there's some notation, and basically what we are doing here, we are looking at for particular the entity I, excluding that because we want to find its rank. So we look at the remaining m minus 1 entities, and what we are looking at, that we are looking at all the subpopulation entities whose confidence intervals is are entirely to the left of the confidence interval for the ith entity. So you know that from this thing, that ith entity, the plausible value for that mean, they likely higher than the means for all the entities whose intervals are below. Okay, and then we are looking at how many intervals will have, how many entities will have interval overlapping. So using these numbers, so those sets and those numbers, um, this cardinality. So rank vector has the joint confidence set given by this set there. And if you look at it, the size of the set is basically dependent on the size of the set lambda oi. Basically, all those entities with overlapping confidence intervals. Okay, and if your estimates are very accurate, there may not be any overlap, and in that case you have a very accurate solution. Okay, so could you please move to the next slide? Here, it's basically from there, this is like an illustration here. If you look at, if you can focus on that entity D, which is corresponding to I equal to 4, and if you look at the confidence intervals there, basically you will see that there are three entities corresponding to 8, 9, and 10. Those confidence intervals are entirely to the left. And then you can also see that I think the entity 3, 5, 6, 7, whose intervals are kind of overlapping with the confidence interval for the item D. So from these things you get for the fourth one confidence set coming out to be 4, 5, 6, 7, and 8. And this way you can, I just illustrated you for I equal to 4, you can check each of them separately, then you can get possible that this confidence set displayed in the previous slide. So could you please go to the next slide? So this is basically the results they have based on that method. So let's go to the next slide and the next one. So furthermore, so now we're going to talk about the Bayesian thing. So the Bayesian thing is basically it's a very straightforward approach. Okay, so just as a counterpart to the frequentist approach that we had in the frequentist approach, the joint confidence set for the thetas, theta 1 to theta m, and using these things we just look at the positions of the different confidence intervals and came up with possible values of the rank vectors. Okay, so we are just doing it the same way, but now we are approaching using a Bayesian approach. So we are corresponding analog of frequentist confidence set is the credible set. So what we do, this is a computational base, we just generate samples of the theta values from their posterior distribution. Okay, that's the main thing in the Bayesian inference. Okay, you have some model, we'll talk about it later on. So from these theta that we have generated, capital S of them could be 10,000 or 100,000 depending on the your computing power and complexity of the model like that. And from those things, we select a suitable subsample. So maybe 90% of 10,000 samples we generated. And those subsamples will have the property, there's some kind of credible set, okay? And then what we're going to do, those say 90% samples of theta vectors, for each theta vector we just rank them, okay, because they are the known values generated for the posterior distribution. We rank them, and by doing this ranking, we just create that rank distribution, and from that we get the credible set. Could you please go to the next slide? So here, for example, a very simple model, okay, like you have this yi's given the thetas, normal theta idea. This is basically the one that the KWW use. And then so that we have their solution as the Bayesian credible set, we are using a flat prior on theta 1 to theta m. If you do that, you can easily check that the joint posterior PDF of theta is multivariate normal, theta I, they're all independent, theta is normal mean yi and variance di, and from that if you create credible interval for theta I, which will be identical to the confidence interval for theta I that we discussed before. So from that thing, we can create an empirical credible set, and from those we look at the sample. Could you please go to the next slide? The sample of like 10,000 to 100,000 we have, then look at the 90%. So next slide, please. Yeah. So so this is basically what we are showing here. A posterior distribution of the rank vector. Okay, so basically we have like 10,000 samples of theta drawn from the posterior distribution of the theta easy, and then for each of these the 10,000 samples, you try to rank. Here the 5 identities, 5 states of US, and we are just ranking. If you look at it, there are 9 different rank types occurring out of these 10,000 samples. So you see that Idaho has rank 5, and then Kansas is 4, Iowa 3. Like that particular vector is like appearing like 34% of the times, and then the rank types, the second type vector like 33%, like that. So from these things, you can actually say that most likely, if you look at the first 4 types, those are the most likely ranks, okay? And particularly if you look at 1, 2, 3, 4, that four rows, that Idaho always rank 5th place. And then the Kansas is ranking between 4 and 3, like that. So so we are going to use this computational approach to come up with the credible set of the rank vector. So could you please go to the next slide? So here, as I said, that you have to create, I said, the central subsample. Like that the credible set, or that joint confidence for theta, we look at it. We basically look at like a box. Okay, so box out of this m-dimensional space. This is like the central part of the m-dimensional space. Same kind of thing. We just select a central subset of the sample of thetas that we have drawn from the posterior distribution. And from those things, that selected set, we said that script f m alpha y, and those selected theta values we are going to rank, okay? And that will be providing us our credible set for the rank vector. So could you please go to the next slide? So what we do, we have these so if you look at a single, an individual element, theta sub S1, it's a vector, M component vector, and you can create a rank, okay? And creating a rank, we're just creating an M by M matrix, a matrix of 0, and then we are just filling out, replacing this whole matrix of 0 by putting some 1. There will be only 1 1 in each column and 1 1 in each row. So totally there will be m ones in the entire matrix. And those positions, basically 1 is indicating the rank, where you place the on the ith column, where you have the 1, and that is basically going to give you the rank for the ith entity, like that. So you just do it this way for all the elements in your central credible set, central subsample, and then you from that you just take aggregate of all those tables, and you get a rank distribution, okay? Probability distribution of the rank based on the selected subsample. That is basically what we call the credible set for the rank vectors. So could you please go to the next slide? Okay, here is basically talking about how to create an optimal credible set, like that. Since I don't have the time, I'll skip that. Please go to the next one. Next slide, please. Yeah, so this is basically about, it's appropriate to talk about Professor Mohananovis. We have our National Statistics Day. So basically you can create, you can select the subsample, the central subsample by using Mohananovis's distance from the posterior mean, and those theta values, sample values, smaller distance, you put it in the your credible set, and from that you just do the ranking. So please go to the next slide. Okay, so keep going. So next slide. Yeah. So this is a simple, as I told you, that this is not necessarily a small area estimation problem. I told you that you can apply this concept, of ranking entities or individuals. So here is ranking baseball players. Okay, something. It's a very popular sport here in US. They are talking about some professional league players from some data, historical data back in 1970, and they looked at this for the season. They look at uh, part of the season data. Based on that, estimated the players' ability, and then they did you can use that, you can do the ranking, we use that data. And also at the end of the season, entire season, you can see the players' performance, and you can take it as the gold standard, the true values. It's not really true values, but sort of like that. And you can compare your solution. So please go to the next slide. So this is basically the solution we talked about, and then we also have our own solution. So please go to the next slide. So next slide, please. Yeah, so what we have here, that basically that the frequentist solution and our Bayesian solutions, in a plot here. You see these like orange line segments, they are stretching. So these are basically the confidence set for rank for each individual players. Okay, joint confidence set. So you have P1 through P18. And if you will see that, I'm sorry that this on the vertical axis, you have 1 through 18. The only thing you can't read it. So those are the possible ranks these players can have. And you can see this orange line segment, all these, for all the players, these segments actually stretching from 1 to 18. So basically saying that the possible rank for player 1 could be anything from 1 to 18. Even for player 18, which is kind of not so good a player, it can also potentially be the best player. Okay, that's the orange line segment, that's the frequentist solution. So what we have, this like pink that's circles that you see there. So those are basically wherever you have these pink circles, some of them, kind of big, then getting smaller and smaller like that. So those dots where we have, basically those are basically the possible values of ranks based on our Bayesian solutions. And if you look at it, the Bayesian solutions is kind of much narrower than the frequentist solution. And Bayesian solution is even saying that if you focus on, say, player 1, is saying the player 1 is the best player. So its rank is like 18, or it could be 17 or 16, 15, like that. And then you see that it is saying that the player 1, which is kind of the best player, is very highly likely he ranks 18. And that big circle, basically that's proportional to the probability. Okay, and then next rank 17 will have probabilities smaller than having rank 18, like that. So, and same way for the other players. So this is basically just simple illustration of showing that the Bayesian method is a very competitive method. Okay, so could you please go to the next slide? Yeah.
Professor, another 5 minutes, please. Another 5 minutes.
Okay. That's okay. Okay, go ahead. So this is basically about this the commuting time data that we had initially. I discussed that thing. So we are going to talk about our Bayesian solution. So could you please go to the next slide? Okay, so that's basically I copied again from the frequency solution from their paper. So the next slide and the next one. Here, you know that basically we have summarized something. So please go to the next slide. We have our figure there. So again, you know, this figure is very similar to the one we had before for the baseball players. Now what we have, the colors actually change. So anyway, this pink line segments, okay, and you see that orange kind of circles there. Those pink line segments are basically giving you the ranks for different states, okay? Confidence sets of ranks, the frequencies method. And then along each line segment, you know, within each line segment, you can see like orange circles there, okay? And those circles are kind of, it's not all over the entire line segment. You can see that it's only over the subset of it. So this is basically showing that again, the Bayesian solution is kind of more focused, more concentrated, more accurate. So that's basically a demonstration of that our method is working. Okay. So could you please go to the next slide? Um, let's go to the next slide. Okay. Yeah, again further down. Yeah, so it is the same slide that I showed you before. So please go to the next one. Yeah, what I have here, so based on the previous thing, what I have, I just looked at showing you a subset of 51 states we have, like 9 sub-states here. And for these 9 states in this table, if you look at the second last row, it is providing you the confidence set of ranks for the state Idaho or Kansas or Iowa, like that. You see that 4 to 9, 3 to 9, and like that 1 to 6. Basically, if you look at it, all of them has the number 4 in this that interval. Okay, so basically we're looking at the states which can potentially receive rank 4. So those are the 9 states there. And then what I have inside the table, we are showing that, for example, if you look at Idaho, that very first column, it can rank only 9, and there is number 100. Basically, our Bayesian solution is saying that with 100% chance that Idaho can rank only 9, whereas the frequency solution is saying that it can rank anywhere from 4 to 9. Or if you go to the rightmost column corresponding to SD, South Dakota, and you see that second row, the second last row, bottom row, it is showing the possible frequencies rank for South Dakota is 1 through 6. Whereas that corresponding column, you see that this green shaded, that's basically saying 3 possible values, 1, 2, or 3. And one can have the probability like 62%, other is like 37, and rank 3 is kind of very less likely, and 4, 5, 6 are not at all possible. So you see that the frequency solution is a little bit wider compared to the Bayesian solution. So please go to the next slide. Yeah, next one. So this is another example. Since I don't have a whole lot of time, this is for the median income. The same kind of the figure I started with. So please go to the next slide. Let's see what I have. Again, you know, this is same kind of plots I have here. It is basically showing that orange line segment is showing the frequency solution of the ranks for various states, their median income of household. And then on the orange color line segment, you can see there on few ranks, you see like a pink circles there. Okay, so this is again like for example, if you go to the rightmost one corresponding to the state of Connecticut, which is sort of like one of the richest states in US. So it can rank from anywhere from like the frequency source anywhere from like 15 to 51, something like that. Whereas the Bayesian solution is saying that it can rank most likely 51, 50, 49, or maybe 48, like that. And it's highly likely it will rank 51. So this is basically again an example of that the Bayesian method is producing uh, better quality solution. Okay, so please go to the next slide. Um, okay, I don't have the time for this topic. So anyway, to summarize, basically we provided an alternative approach to the frequentist method of creating a joint confidence set of ranking, which is important. You know, you can apply it in um, government publications, or you can do it just ranking players like the batsmen or bowlers, like that. You can apply this thing. You can both have a frequentist method. You can both have a Bayesian method. So this is kind of a very general kind of approach. And so I like to basically stop here so that you have some time to ask questions
Yeah.
or like that. But thank you very much for inviting me. Okay, I really appreciate it. Thank you.
Thank you, Prasad. Thanks for your wonderful presentation. Now, due to shortage of time, I think one or two quick questions. If anybody is having a clarification or comments, please. I think a very good topic, small area estimation with using Bayesian concept, the important areas.
Yeah, but we can apply this thing like Joya's presentation. She was looking at this breast cancer
Yeah.
in different countries in Southeast Asia or South Asia, and based on suitable model,
correct.
we can get Bayesian. This approach is kind of very general. Okay, you can apply it anywhere. I just focused it on small area estimation because when I got exposed to this thing, this colleague of mine at the Census Bureau, that's kind of small area estimation application. Yeah.
Thank you, Professor. Thanks for your nice presentation. I think let us give a big hand for Professor Gauri. And now we are coming to the end of the session. And now it is before handing over the podium to Professor Sadish. So I thank all the speakers, both the speakers from US, they've taken all the time to this one. And one is on cancer epidemiology, other one is on small area statistics with using Bayesian approach. Really two wonderful topics for youngsters who are working particularly in India. With this, I thank both the speakers on behalf of me as on behalf of the organizers. Now I thank Professor Satish Kumar also for requesting me to chair the session, the wonderful session, because I had connection with even our Florida University as well as the other thing, because I'm basically from Brown University, so I know most of the people are sitting there. So with this, I thank both the speakers and all the audience for their presentation. Now over to Professor Satish Kumar. Thank you, Professor.
Thank you, Professor Jaya and Professor Gauridetta, for your wonderful talks.
Thank you.
And also, we wish to extend our gratitude to for nice the session and for supporting us through chairing this session.
Okay. Thank you.
Now, let us move to the next session. We are very much grateful to each one of you, professors. Sandra, please introduce the chair and support the chair to run the session smoothly.
Good evening, everyone. On behalf of the organizing committee, a warm welcome to all of you to technical session number 20. Keynote session in honor of KCS Pillai of WSTA 2026. 11th International Conference on Recent Trends in Statistical Theory and Applications. It's my pleasure to introduce our session chair, Professor Arun Kumar Sinha from the Central University of Bihar, India. Professor Arun Kumar Sinha is a distinguished statistician and academician with extensive experience in teaching, research, and higher education. His research interests include probability distribution, statistical quality control and improvement, order statistics, environmental statistics, statistical computing, design of experiments, business statistics, statistics learning, data mining, etc. He has published numerous research papers in reputed national and international journals, supervised doctoral scholars, and has made significant contribution to statistical research and academic development. We are honored to have Professor Arun Kumar Sinha chair this keynote session and look forward to his valuable guidance throughout the proceedings. I now have the pleasure of introducing the keynote speaker for this session. Our keynote speaker is Professor Thomas D. Kusbowski from the University of Nevada, Reno, USA, who will deliver a keynote lecture on multivariate distributions and processes under multiple scaling regimes. We look forward to an enlightening keynote address and an engaging session that will provide valuable insights into this important area of statistical research. I now respectfully invite Professor Arun Kumar Sinha to kindly chair this keynote session and commence the proceedings. Over to you, sir.
Professor Sinha, unmute your mic.
Professor,
Sir, unmute your mic. Professor Sinha, your mic is muted.
Professor, your mic is muted, so please unmute the mic. Professor, Professor Sinha, the mic is muted. So click on that audio button. We couldn't hear you, Professor.
He is not unmuted.
Please unmute mic.
I think Pallavi or somebody can talk to him on that.
Okay,
Ask
I
him to
shall
unmute the mic.
hold.
Professor, you may have control over the unmuting or muting your from the worst will have the controls. Right.
Professor?
Again he muted. Ask him to click once again.
Okay. I think it's okay now. There's no
Oh,
problem.
it's okay. It's fine. It's fine.
That's okay. Thank you. Thank you. Following a graduate study of applied mathematics and at the University of Warsaw, Poland, Thomas J. Kozubowski received a MS in statistics from the University of Texas, El Paso, and PhD in statistics from applied probability from University of California, Santa Barbara. He is currently a professor in the Department of Mathematics and Statistics at the University of Nevada, Reno. Dr. Kuzowski works in the general area of stochastic modeling of natural phenomena in variety of fields, including climatic research, geosciences, finance, and economics. His research interests include the distribution theory, Laplace distributions, and the generalizations and limit theory for random sums, heavy tailed distributions, extremes, mathematical statistics, financial and insurance mathematics, stochastic, models for hydroclimatic phenomena and fractal scaling processes. He has authored 2 monographs and over 100 research papers in probability and statistics. Dr. Kozubowski is currently an editorial board member of several academic journals and an active researcher, having referred for many of over 100 different academic journals. With these, with the 2016 Sentinel of Science Reward, he was received by Poulons, and one of the researchers contributing to the peer-reviewed in the field of mathematics. So this is a brief description. I would request Professor to begin his lecture.
Thank you very much for your introduction. Can everybody hear me?
Yes, I think everything is very
Can
clear.
you hear me? Can you confirm? Thank you. So thank you for your introduction. Thank you for your kind invitation to attend these sessions. I will begin momentarily, but you have to tell me how to upload the presentation, because I don't know how to upload the presentation on the screen.
In the bottom there, first you open the file, and then at the bottom there is an upward arrow, small box. There is an upward arrow. Click on that.
And what does it say on this box?
Yeah.
Which one?
A small box with upward arrow. A small box near to the camera button.
There is camera, there is share screen. Okay, okay.
Yeah, share screen. Yeah.
Okay.
Share screen is there. Next one.
Yeah. Next.
Yeah.
Share screen.
Then a small box pop up.
Yeah, one upward arrow is there.
Yeah, in which you have.
Momentarily. Entire screen?
Yeah, entire screen.
Entire screen. Okay, and then what? Allow?
Slides. Then move to the slides, and then share button. Share button.
Can you see the screen?
Yeah, we can see the desktop of your computer browser.
Okay, but I need to, I mean, the presentation is open.
Yeah. You have
Let me
to.
go to it. Can you see it now?
Now it is fine. We can see the presentation first.
You can see the presentation, is that right?
Yes, it's fine. It's fine.
Okay, I don't see the meeting room anymore, but if you see the presentation, that's good enough. So let me get started then. Thank you.
Yeah.
Okay, so first of all, this is a joint work with my former student, Amos Natido, who's now a professor, University of California at Santa Barbara. So I'm first going to give you an outline of what I will be presenting. So we shall start with generalized Laplace distributions very briefly, and then discuss ways of generalizing these distributions into more general settings. There are generally two ways of generalizations that have been introduced to the literature. One of them is what we call dimension-wise Gaussian mixtures. And then the second approach is called multiple-scaled Gaussian mixtures, that both approaches lead to many different models that can be useful in multivariate data analysis. So we will focus on the second approach, multiple-scaled Gaussian mixtures. We're going to go over some key properties, and most importantly, infinite divisibility of this setup, which leads to further extensions to stochastic processes and applications. And then at the end, we're going to give a brief summary of these results. So to get started, we're going to talk very briefly about generalized Laplace distribution and more generally Gaussian mixtures. So what we're looking at on the screen in figure 1, on the left-hand side are the densities, couple of densities of what is known as generalized Laplace distribution. So the characteristic feature of this distribution is a very high peak, very sharp peak in the middle of the distribution. That's at the mode. And the tail of the distribution is somewhat thicker than that for the normal distribution. So these distributions are very useful in many applications, spanning in engineering, communication, signal processing, image analysis, and so on. In economics, they've been used to account for asset returns data and so on. On the right-hand side, we're looking at bivariate plot of bivariate Laplace distribution. Now, this distribution is an example of the general concept, a Gaussian mixture, which we're looking at right now in Formula 1. So essentially what it is, we're looking at the Gaussian distribution X. That one is centered at 0, so it's with the mean 0 and some covariance matrix, sigma. And then this Gaussian distribution is also scaled by a random weight. It's a square root of W, where W is a non-negative random variable. So in the symmetric case, this is it, just square root of W times X. A skew distribution comes up if there is additional term in the middle where we have W multiplied by some vector. So mu and eta are deterministic vectors that represent the center of the distribution. This is mu, And eta has to do with the skewing mechanism. So for eta equals 0, we get a symmetric distribution. And for general eta, we get like an asymmetric or skew distribution. So this model is very, very popular for the last many decades, with applications spanning many different fields. These days, these Gaussian mixtures are very popular models in clustering and classification and so on. Well-known distributions that arise in this setup are, for example, T-distribution. Students' T-distribution is a member of this class. For the student T-distribution, this random scaling factor W basically follows inverse gamma distribution. The Laplace distribution arises when W follows exponential distribution, and when W follows Laplace, when it follows gamma distribution, then we get what is called generalized Laplace, also known as the variance gamma model. So informally, we can think of it as a normal, it's a conditionally Gaussian distribution. So given W, it's a Gaussian distribution, but the unconditional distribution can be expressed as the Gaussian with the random scaling, basically. All right, so this is the background information about Gaussian mixtures, and some limitations of these mixtures are discussed next. So, okay, before I go there, let me just briefly mention some limitations. So because of the way that we scale the Gaussian distribution, the same factor W basically appears across all the dimensions. So for each coordinate of X, we multiply by exact same square root of W. So because of that, this class of distributions is somewhat limited. So different coordinates essentially will follow basically the same distribution. So for example, we couldn't have a Laplace distribution for the first coordinate, or T distribution of the second coordinate, or normal distribution on the third coordinate, and so on. So we want to relax this condition of the same distribution along each coordinate. We want to have different distributions, possibly along different coordinates of the random vector y. So to achieve this goal, there are two mechanisms that have been proposed. The first one is called dimension-wise Gaussian mixture. So I will discuss this one first, again, very briefly, because we want to focus on the second one. So let me point out this publication back from 2003, so it's over 20 years old. This publication is perhaps one of the first or the first place in the literature where this methodology has been originated. Okay, so back in 2003, this paper was published, and they proposed these different approaches to generalize Gaussian mixtures, including this one. And then for at least 10 years, nobody really picked up on this. And then about a decade ago, there was a boom of papers related to this construction. And these papers actually were not even aware of this key publication. So here we're looking at formula number 2, where we have the new formulation of this extended Gaussian mixture. So essentially what we're doing is we take the Gaussian vector x, the same as before, but this time we basically multiply each coordinate of x by different w. So there is a whole vector of w's, w1 through wk. K is the number of coordinates of x. and each W is multiplied by different xi. So this can be written as a diagonal matrix of W's. So we have a matrix with W on the diagonal, and this matrix is multiplied by the column vector X. And then possibly we can add a centering constant mu, which is another k-dimensional vector. We can also introduce a skewing mechanism as well. All right, so this is the dimension-wise Gaussian mixture. And again, this W, don't really has much restrictions. It can be any random vector whatsoever. It can follow, these W's can follow the same distributions or different distributions. They could be dependent, independent, and so on. If all the coordinates of W are the same, if all this Wi is one and the same W, then this goes back to the standard Gaussian mixture. So standard Gaussian mixture is a special case. Now, the second model that we will talk about is closely related to the spectral representation of the covariance matrix sigma of the underlying Gaussian distribution. So to introduce the second model, we're still talking about the first model that can be written in a slightly different way, starting in bullet number 1 with a representation of Gaussian. So Gaussian X can be written as the square root of the covariance matrix times a vector Z of standard normal random variables. So we just take standard normal random variables and multiply by the square root of the covariance matrix. And the covariance matrix can be broken down into this product given in formula number 4, very well known spectral representation of matrices. So basically, it has to do with eigenvalues, lambda j, and eigenvectors dj. So there is this eigenvalues, lambda 1 through lambda k, and these eigenvalues have the eigenvectors d1 through dk. These dk's are orthogonal vectors, so basically we can put them together in a matrix form. This matrix form is the matrix capital D. So the columns of D are the eigenvectors of the spectral decomposition of matrix sigma. Okay, and using this concept, we can revisit the representation that we looked at earlier, and we can write it as formula number 5. So in formula number 5, we're still looking at this diagonal matrix delta W to the power half, and then this diagonal matrix is multiplied by the normal vector X, and this normal vector X appears there in formula number 5 as D times lambda to the power half, where lambda is the diagonal matrix of eigenvalues, and then the vector of IID random variable Z. All right, so this is the way we can write this representation. So let me just say that the second approach, the one that we're going to focus on, is very similar to 5. It looks very similar, except we interchange the order of multiplication in this representation in such a way that the matrix D will gonna be first, and then in the middle we put this matrix delta W. Okay, so we're moving with the second approach, multiple scaled Gaussian mixtures. So here we are in formula number 6 is the definition of multiple scaled Gaussian mixture. So in this representation, the new random variable is on the left-hand side. That's the random vector y. On the right-hand side, we have a centering constant mu in addition to these matrices that there are 4 of them. So the first one is the same matrix D from the spectral representation. The second matrix is the square root of the diagonal matrix of eigenvalues. The third matrix is the diagonal matrix of the random vector W. These are the weights. And then finally, the capital Z is the vector of IID standard normals. Okay, so this is the model we're talking about. This is a conditionally Gaussian model. So if W's were given, then this is a Gaussian random vector with the appropriate covariance matrix. But this one has a stochastic covariance matrix. So we can think of it as a Gaussian with a stochastic covariance matrix, and the stochasticity of this matrix comes from the random variables W. So you can think basically of putting like random eigenvalues. So eigenvalues become random variables now. We put them along the diagonal in the middle of this multiplication. So there is a lambda times delta W. This is a diagonal matrix, and on this diagonal, there is lambda J and Wj. Okay, so the stochasticity comes from the distribution of W, and one particularly convenient way to express this relation in Formula 6 is to write it explicitly in terms of Formula 7. So let us spend a little time on Formula 7 to see basically what we're doing here. So it's a summation from 1 to k. And in this summation, we have some constants and we have some random variables. So the first constant in this summation is the vector dj. Vector dj represents a direction in space. It's a deterministic vector, not a random vector. And then along this direction in space, we multiplying by a scalar, lambda j, square root of lambda j, and we also multiplying by the standard normal zj, as well as square root of wj. So basically what we're doing is we are doing a Gaussian mixtures along the direction dj. So along a particular direction in space, we have a Gaussian mixture. So if we didn't have Wj, it would be just a normal distribution, but we go beyond normality by this random factor Wj. So in a way, what we get out of this is a vector sum of these components. So each component is a vector. We take the vector sum of these components, and basically that's how we get the random vector y. Okay, very good. So, so moving on, here is a attempt to illustrate this. This is reminiscent of the standard approach in multivariate statistics when we decompose the normal distribution into principal components. It's very similar approach, except that now these eigenvalues have to do with W, they become a random variable. So the randomness is not connected with the regular coordinates of Y. This randomness is connected what's going on along the eigenvectors in the spectral decomposition of the matrix sigma. So using this approach, people have derived various things. There's actually quite a bit of literature along these directions. I've listed a couple of papers here back from 2014, 15, and so on. people have studied this. And when we look at this research, we noted one particular aspect that that we wanted to basically generalize and comment on. So the problem with this model is that the matrix sigma may not actually act as a parameter of this model. The problem is that the model may actually depend on the actual choice of the eigenvectors corresponding to eigenvalues that have multiplicities more than one. So if all the eigenvalues of the matrix sigma are distinct, then what happens in this case is that the model is uniquely determined by the matrix sigma. However, if there are some multiplicities that come with these eigenvalues, then the model is no longer uniquely determined by the matrix sigma, and essentially we wanted to fix this. So we propose an adjustment to this standard approach by taking into account the fact that eigenvalues may have different multiplicities. And as a simple example, we're looking at the bottom of the screen. This is the case of 2 dimensions. So if we only have 2 dimensions where the matrix is 2 by 2, so we can take for simplicity the case of diagonal matrix 1 and 1, and with 2 eigenvalues and so on. And if we work out this model in such a case, then there is a choice on how to take these eigenvectors, D1 and D2. There's a lot of choices for those. And consequently, the model that comes out of this, given by formula number 9, clearly will depend on the choice of the eigenvectors. So it basically depends on the parameter theta that determines the eigenvectors. So what we want to do, we want to reformulate the whole model in such a way that this dependence on the choice of individual eigenvectors is no longer there. Okay, so this is summary of these points. The distribution of this construction basically may not be uniquely determined by the covariance matrix of the underlying multivariate normal distribution. So it cannot serve as a parameter of this model, contrary to what is typically assumed in the literature. We want to modify this framework so that this is no longer the case. We also want to point out some fundamental properties of this model, including infinite divisibility. And in particular, we want to highlight the fact that these distributions may be infinitely divisible and lead to very interesting stochastic processes that can be studied in this context. So the formulation of this modification is somewhat technical, but essentially what it is that when these eigenvalues have multiplicities greater than 1, then we treat these eigenvalues like in the single group. We put them together as a group, and within this group, we look at the entire eigenspace built from all the eigenvectors corresponding to these eigenvalues within a single group. And then for this entire space, like a subspace of Rk, we assign one and the same W instead of bunch of Ws, one for each eigenvalue. So these eigenvalues basically are grouped. Here is the write-up for this. We assume that they are L distinct groups of eigenvalues, lambda 1 through lambda L. And for each one of these lambdas, there may be multiplicity kj. This kj may be 1 or maybe greater than 1. All these multiplicities must, of course, add up to the dimensionality k of the space. So for each lambda j, they are precisely kj linearly independent orthogonal eigenvectors, d1 through dkj. They span some subspace Sj over k, and all the subspaces that correspond to different eigenvalues are mutually orthogonal. So what happens here is if within each subspace we pick another group of orthogonal eigenvectors, so basically another basis that span the same subspace, and we formulate a matrix based on both of these bases, then what is important is that the quantity, when we multiply V times V transpose, or V tilde and V tilde transpose, then we always get the same result. Okay, so this is formulated down below as lemma, basically independent of this whole model. It's just a result from linear algebra. If we have L orthonormal vectors in Rk, where L is less or equal than K, so basically in this case, and if we pick another set, V1, VL tilde, that span the same subset of the Rk, then the two matrices V and V tilde have this property. So if we put these vectors as columns, so we have V1 through VL, that is V. V tilde is the same construction from the VI tildes. And then the product of V times Vt and V tilde times V tilde transpose are always the same. Okay, so this result from linear algebra we basically use to prove that in this new formulation of the model, this model depends entirely of the matrix sigma in case when multiplicities of the eigenvectors exceed 1. Okay, so there is quite a bit of information in this presentation. I think I will focus on the most important result about being infinitely divisible. So before we get there, let me just share how this model can be written explicitly. So on top of the screen, we get the traditional formulation where we take into account all the eigenvalues lambda j, and for each eigenvalue lambda j, we assign different wj. So that's the traditional approach. And then the new approach is given by formula number 10, where we still have a very similar formulation, but you notice that instead of the vectors dj, we now have matrices dj, and instead of univariate normals zj, we have bold-face zj's, which are vectors that are normal. Okay, so it's very similar formulation, but the advantage is that we will have much fewer parameters in this model if the multiplicities of the eigenvalues are greater than 1. The number of w's will be greatly reduced. So in this setup, so this is kind of extension of this traditional Gaussian mixture in k dimensions, leads to very interesting probability distributions. We can use variety of choices for these w's to come up with different kinds of models and so on. The major challenge, of course, in this entire area as you may imagine, is parameter estimation. So the models can be formulated and they follow some structure and so on, but identification of the model, parameter estimation, and so on is a big challenge in this area. Okay, here's another formulation of these Gaussian mixtures. We're looking at formula number 12. So this is probably the most compact way that we can write this. So there is a matrix X and there is a W, boldface W in there. This X is a matrix that has L columns, X1 through XL, is a K by L random matrix. And the columns in this matrix are independent and orthogonal multivariate normal random vectors that are explained down below. So these xj's basically are mean zero normals, where the covariance matrix is precisely equal to dj times dj transpose. And because of the lemma we saw earlier, this dj times dj transpose will always be the same matrix regardless how we pick the eigenvectors within the subspace. So this representation, of course, is equivalent to what we saw earlier, which is the formula in the middle of the screen. All right, so this is, I mean, we spent quite a bit of time just to explain this construction. Now we're gonna spend the rest of the presentation. We have about, do we have 5 minutes or how much time do we have? It's a question. Okay, I'm assuming that there's 5 minutes. May be wrong, but I have to assume something. So yeah, so this is the formulation. Now we move on with some properties. Again, we're not gonna check all of them because there's limited time now. But let me just say that by doing conditional arguments, so by conditioning on the distribution of W, one can essentially develop the whole theory and many interesting properties of these models. Things like probability density function, formula number 13. For independent components, these W's could be independent. If they are independent, the formula will simplify to number 14 and so on. In the very special case, when all these W's are equal, we basically getting the PDF of the traditional Gaussian mixture given by formula number 15. The covariance matrix and moments can be calculated as well. I want to point out formula number 16, where we're looking at the covariance matrix of the random vector y. This covariance matrix may be related to sigma, actually. And in fact, if the random weights W, if they all have the mean equal to 1, then formula 16 will reduce to the covariance matrix sigma. So sigma is really the parameter of this model, and it works as the covariance matrix as it did for the Gaussian distribution. So there are many properties. I will skip over some of them. Here are linear combination of the components. The linear combinations are traditional Gaussian mixtures, one-dimensional mixtures, and so on. The characteristic function is extremely important here because it will decide whether the distribution is infinitely divisible. So formula 21 actually provides the characteristic function of this particular distribution. And in this formula, the main thing to note is the function phi w. This phi w is the Laplace transform of the vector of w's. So if this Laplace transform is in, I mean, if this distribution of w is infinitely divisible, then we can take the power of this phi w. And when we do, we can prove that this distribution itself is infinitely divisible. So let me just say a few more words about this infinite divisibility, which is the key property of this model. And when we describe this infinite divisibility, we will also note another interesting representation of this entire distribution. So we're looking at this stochastic representation starting with the random vector w that follows this distribution. So to formulate the stochastic representation that is given by formula 24, when we look at formula 24, it has a very simple form. Actually, it's a stochastic process X subordinated to the random vector W. So the question is, what is the stochastic process X? The stochastic process X is provided by formula 23. So in this stochastic process representation, the input T is actually a vector. It's a vector of constants from T1 through TL. And this Gaussian process xt can be defined by a bunch of Brownian motions. So the Brownian motions here are denoted by boldface bj. This is a Brownian motion that is built from the normal distribution, where the covariance matrix is basically a diagonal matrix where on the diagonal there is lambda j. So lambda j are identical eigenvalues of this original covariance matrix. So there is this lambda j, and then multiplied by identity matrix and so on. So we have this Brownian motion, which is k-dimensional, and this Brownian motion is multiplied by the matrix dj, which is the deterministic matrix. So once we define the stochastic process xt, we basically replace this constant t with the vector w, and that's exactly how we get the random vector y. Okay, so it admits a very interesting and important stochastic representation as a subordinated stochastic process. Okay, so I think we will probably stop the theoretical explanation here. I'm going to skip through a couple of things because we don't have time. Let me just share with you some graphs here that can provide some insight into how these multivariate distribution look like. These are three-dimensional plots of the densities of a particular model where this W follows gamma distribution with parameter alpha. Okay, so that would be direct extension of the generalized Laplace distribution. The next plot shows density level curves. So let me point out that the densities are not the level curves can be, but they don't have to be ellipsoids. They can have very different shapes as illustrated by these graphs. So this includes here some non-symmetric distributions. All right, so we're gonna end with the summary. We considered a pretty interesting new class of mixed multivariate Gaussian distributions for modeling multivariate data that may exhibit different marginal distributional properties. So this model incorporates the traditional location scale mixtures of normal distributions, but these constructions of the Gaussian mixtures basically are applied to the eigenspaces corresponding to distinct eigenvalues. And these components are typically multivariate in contrast with the univariate case studied in the literature. By allowing dependence among the random weights, we construct dependent building blocks diverging from independent structures commonly assumed. The resulting distributions are fully determined by the underlying scale matrix sigma and are invariant under the choice of eigenvectors associated with eigenvalues of multiplicity greater than 1. So this construction results in models with significantly fewer parameters compared to the standard approach, includes traditional location scale mixture of normals as a special case if all the W's collapse to the same univariate random variables. These level curves of the density are generally not elliptical, and the tail behavior and kurtosis may differ along each principal direction. And key property preserved in this framework is infinite divisibility, which holds whenever the vector W is infinitely divisible. And this property further enables the construction of multivariate Levy processes in the spirit of Laplace motion. Okay, so this brings us to the end of the presentation. Here are some references for anyone interested in this to read further these developments. There's a bunch of papers along this direction, starting with paper 1 on the top of the screen, where you can find definition and more information about Gaussian mixtures. Okay, so thank you for your attention, and I hope that I made some sense here. Okay, let me go back to the room. Should I stop?
For your nice presentations. And I think if somebody has asked some questions, they should be invited to say something or put questions to the speaker. And he has his email address, so he could also be contacted through email.
Yes, please. If any questions come up later, please don't hesitate to email me.
Yes, yes.
For references or any ideas or any questions.
It is easy to contact you through email. If he has some interest, there's no problem.
Yes,
so
Professor Satis has my email. I can share my email maybe in here somehow.
Yeah.
Please.
That is nice, because there is another session after this one. So I thank the speaker as well as the organizer, Satish, for nice presentation and as well as good management here. I thank participants also for nice presentations, because in the era of environmental sciences, environmental investigations, this work could be very useful, I hope.
Thank you very much for the opportunity to present.
Thank you so much.
Thank you.
Thank you. Have a nice weekend.
Yeah, I'm gonna be traveling tomorrow, so.
Thank you so much.
Thank you.
Thank you. Thank you.
All right. Very good.
Thank you, Satish.
Yeah. Adira?
Yeah, you have another session you have, I think.
Yeah. Now one more session with one more session with the two speakers, I think. Then we can morning. Tomorrow also we have to.
Yeah, Satish must be very tired in doing everything from morning to late evening.
Yeah, brother. Tightly scheduled. Yeah.
Yeah.
Yes, sir. You must be very tired. We are very thankful, sir. So you are doing all. We are very thankful, sir. We are getting so many. We are learning so much, sir.
Thank you.
Thank you so much, sir.
Thank you. Thank you. Thank you very much. Adira, now let us move to the next session. Okay.
Okay,
Adira,
sir.
please. Thank you, Professor. Thank you for chairing this session.
See you tomorrow.
Yeah. Yeah. Okay.
Good evening, everyone, and a very warm welcome to this technical session 21 of WSTA 2026. It's our privilege to have Dr. Neha Garg, professor in the discipline of statistics at Indira Gandhi National Open University, New Delhi, as the chairperson for this session. Dr. Garg brings more than 19 years of distinguished experience in teaching, research, and academic program development, with significant contribution to estimation and sampling techniques, self-learning materials, and statistical education. We are equally honored to welcome our esteemed invited speakers, Professor Poonam Singh from the University of Delhi, whose research contributions have greatly advanced the field of statistics and data analytics. Dr. M. Tiwari from Sultan Qaboon University, Oman, an accomplished academic known for his expertise in statistical methodology and applied research, and Dr. Darba Bhattacharya from St. Xavier's College, Kolkata, whose work span mathematical statistics, statistical inference, and interdisciplinary applications. With great pleasure, I invite Dr. Neha Garg to chair the session and warmly welcome our distinguished speakers to begin today's proceedings. Over to you, ma'am.
Thank you so much, Atira. Have the speakers join? I think speakers are yet to join.
I shall check. Darba Bhattacharya already informed me she will be here. Just a minute, I have to check.
Yeah, I think Durva Bhattacharya has joined. So I think we should start the session with her. So let me first from the Indian Statistical Institute, Kolkata in 2018. Dr. Bhattacharya has over 20 years of teaching experience. Her research interests include Bayesian non-parametric modeling, statistical genetics, Bayesian computation, biostatistics, multi-objective optimization, and machine learning. Now, on the behalf of organizing committee and on my personal behalf, I welcome Dr. Durba Bhattacharya to this session. We are very eager to hear you, ma'am. You have around 30 minutes for your presentation. Please share your screen. Please unmute.
Thank you. Thank you so much for your kind words. Thank you, Satish sir. Thank you, Professor Garg. I'll just try to, I'm trying to share my screen. Yeah, is my screen visible?
Yes, it is visible.
No, it's visible. Okay. So
Is
I'll
it in
just,
presentation mode?
no, I'll keep it. I'll put it in presentation mode. Just a thing, I'm just putting my video off because of like network issues, so that I can present it better.
Yeah, please.
Yeah.
Please.
Hello, I hope I'm visible.
Yes, yes, it is visible.
Screen is visible. So,
Yes.
hello everyone. I'm Durga Bhattacharya from St. Xavier's College, Kolkata. And thank you very much, organizers, for inviting me to this 11th International Conference on Recent Trends in Statistical Theory and Applications. So I'll be presenting on statistical learning with infinite dimensional priors. And this session is extended to be an introductory session on Bayesian nonparametrics. And we will be focusing on Dirichlet process prior as an infinite dimensional prior. So we will try to understand why we may actually need Bayesian nonparametrics and how we can manage to understand and use it. So by the end of this discussion, we expect to be able to understand why nonparametric Bayes is challenging, but it is one practical thing to do. So we are going to focus on particular problem of clustering or mixture models and a particular non-parametric model based on Dirichlet process. So now, although Dirichlet process is not whole of the non-parametric Bayes, it will help us understand the intuition behind the usefulness of non-parametric Bayes, I'm sure. Now, if we proceed, so we can see any statistical problem solving, for any statistical problem solving, we depend on data. So data are envisioned as realizations from a collection of random variables. It can be y1, y2, yn, and yi's are thought to be governed by some probability law, which is G. This is according to this probability law, we are generating data. So when does a statistical problem start? A statistical problem begins when we have some uncertainty about this probability law. Right. So if we consider, if this small g theta is considered as a PDF from a family of distributions, so G can be labeled by a set of parameters theta, right? Belonging to a parametric space, capital theta. So if capital theta can be generated by finite dimensional basis vectors, we say that this is a parametric model. Now, what is it? There are some disadvantages of using parametric models, as we all know. So if you use parametric model, it is basically constraining the inference to a specific parametric form. So it is limiting the scope and type of inference that can be drawn. So we may want to relax the parametric assumptions to allow greater model flexibility and robustness against model misspecification. Then we have what is known as non-parametric approach, right? So in frequentist parametric approach, we assume that the data is being generated according to some probability law with a known mathematical form governed by a certain number of finite dimensional parameters theta. When we assume, so if we want to have more robust inference, then what we do is we consider models where the class of densities is not specified, like through a mathematical form, right? So we just say the class of densities is F, where F is a probability distribution with some general regularity conditions. Right, so you see, there is no specific distributional form which I'm assuming here. Distribution is estimated directly from the observed data, right? And more flexible for complex and unknown data generating mechanisms it is. Okay, so what kind of so we all are familiar with frequentist non-parametric approaches, which are done through empirical CDF estimation, then kernel density estimation, splines, etc. Right? Now we are moving to Bayesian parametrics. So what is Bayesian parametrics all about? So in Bayesian parametrics, we have a joint model on parameters and data, as you can see, which is this probability of parameter theta along with the data. This is written as the sampling model, that is the likelihood, multiplied with the prior, right? So what are the elements of Bayesian parametrics? We have observed data, we have unobservable parameters which are finite dimensional, and combining these two, combining the sampling model and the prior belief on the parameters, we have posterior distribution, something like this, right? We can summarize the posterior. So this is what is known as Bayesian parametric inference, right? Now, non-parametrics, now when we are going for infinite dimensional prior, we are going for statistical learning based on infinite dimensional prior. What do we mean by that? So we are slowly heading from Bayesian parametrics to Bayesian non-parametrics. So what do we mean by, so what is the difference between a frequentist non-parametrics and Bayesian non-parametrics, right? So in Bayesian non-parametric, what capital F, this distribution function itself is a random probability distribution. So historically, frequentist non-parametric methods came first. We all know, we are familiar with frequentist non-parametric methods. For example, like we said, empirical distribution, kernel density function, etc. So now when Bayesian statisticians later asked that can we do Bayesian inference without assuming a finite dimensional parametric family? So they had to formally define probability measures on spaces of functions. So what is my parameter under Bayesian non-parametrics? My parameter is the probability distribution itself. So now Bayesian people, they put priors on parameters, right? So if your parameter itself is the entire probability distribution, what should be your prior? Where should you put the prior distribution? You should be putting prior distribution on the probability distribution itself. So this is so capital F is a function, probability function defined on infinite dimensional functional space, and hence in Bayesian parametrics we have to define probability measure on infinite dimensional space, right? So what is Bayesian non-parametrics? If we focus on this table, we know what is frequentist non-parametric, we know what is frequentist non-parametric, we know what is frequentist parametric, we know what is frequentist non-parametric, we know what is Bayesian non-parametric. So whatever doesn't fall in all these three categories falls into this category of Bayesian parametrics. Okay, so Bayesian non-parametric models and methods are typically characterized by infinite dimensional parameter spaces. Generally, they are, what do we don't know in Bayesian parametrics? What is a parameter? It is the unknown CDF itself is a parameter. It's not that the CDF is parameterized by certain number of parameters, theta 1, theta 2, theta 3. The CDF itself in complete entirety is assumed to be the parameter, or it can be regression function, it can be link function, etc. Okay, so and Bayesian non-parametric models revolve around construction of probability measures over these functional spaces. Okay, so if we want to summarize, under parametric Bayes, how do we proceed? So under parametric Bayes, we assume that this is our data x1, x2, xn. It follows some probability distribution with known mathematical form parametrized by the set of parameters theta, where on theta we assume a prior pi, right? And we combine these two to get the posterior distribution of theta. Now come to Bayesian non-parametrics. Here what we assume? We assume x1, x2, xn follows a random probability measure, capital F. Do you get my point? So F is no more indexed by a set of parameters. F is itself a parameter. The probability function itself is a parameter. So the idea is to define prior probability measure on probability distributions. So Bayesian non-parametrics is all about asking how, it starts by asking how to conceptualize such a prior probability distribution measure on probability distributions, right? And how to get a posterior distribution for F. So posterior distribution under Bayesian non-parametrics will look something like this. See the difference? If you want to visually understand, this is the situation, right? So let us take some problems. So you can consider a density estimation problem. Example 1 is, you see, a density estimation problem with observed data. Suppose yi's are my data points following a random probability measure G, which itself is the parameter. So under Bayesian paradigm, because Bayesians always look for priors, they require completion of the model with prior for the unknown distribution G, right? This is the unknown random probability distribution G, right? Now this G, if you consider G to be a parametric family, then it becomes Bayesian parametric methods. If probability model you are looking for is on infinite dimensional function space G, then it leads to non-parametric Bayesian models. Okay. Now we look at this example. You see in the left panel, if you plot the histogram, we have some data. We have plotted the histogram. Now, if you want to fit a normal distribution, normal θ1 to this data, what is the problem? You will have a unimodal distribution. Not that, I mean, assuming normal is not important. You can assume any distribution with a parametric form, right? So you will only restrict yourself to a unimodal fitting, right? So this is the problem whereas we can see clear bimodal distribution in the data set. So there is limited flexibility if you assume if there is model misspecification, right? Whereas if you assume non-parametric family, in this situation, you see the model learns from data. The data dictates how the model, what the fitted model will be. If you look at this, and if it is visible, I think it is, I'm not sure if it is visible, the dotted lines are, so these are random draws from probability distribution. So when you are doing non-parametric Bayesian, your draws will yield you random probability measures, right? So this is on an average, this will be the probability model, the dark line, and the dotted lines are random draws from the fitted probability model. Okay. Now, if you consider this example of mixed effects model. Okay. So what is it about? So suppose, recall the mixed effects model, y equals to x beta plus zu plus epsilon, right? Where x beta is the fixed effect. This component denotes the random effect and epsilon is the residual error. Now, suppose we are analyzing students' test scores for 50 schools, right? So what is x beta? X beta here can capture the effect of study hours, gender, etc. And what are U's capture? Suppose the school specific effect. So what is our usual assumption in a random effect model? We can assume that U follows normal with certain mean 0 and variance covariance matrix capital sigma. But what if the schools fall into different groups, like it can be elite school, it can be average school, it can be underperforming schools, etc. In that case, what can you expect in that case? Or so the distribution of the random effects will not be normal. Or you can think of 200 hospitals. If every hospital behaves similarly, the posterior for G will look normal. Fine. Now, if the hospital forms several groups, then if you go for normality assumption on random effects, it's not fair for under such a situation. So Bayesian non-parametric methods lets the data learn the shape of the random effects distribution. That's what we are trying to say. Now you take the next example. So if we are doing fitting problem, right? So f is unknown. So if you assume f to be a known form, say f can be some beta naught plus beta 1 x linear function. So this problem is estimating the finite parameters beta naught and beta 1. That is fine. Now, what if this f is unknown? What is the parameter now? The function itself is the parameter now. You cannot say that beta naught and you have a finite number of parameters. No, the function itself is a parameter, and that makes this an infinite dimensional parameter space, right? So Bayesian non-parametric priors can help you out in this situation. Okay, so consider this problem. Okay, so this example I have taken from Gendani et al. It's a published paper in 2012. It's table 2. So the data is given on count of T cell receptors. Okay, so researchers are here studying the number of T cell receptor sequences observed in an experiment. Okay, so each receptor can be 0, 1, 2. It can be observed 0 times, 1 times, 2 times. That is a problem. Now, what is unusual here? If you look at the data, this is zero censored data. This is a zero censored data. So what may be the reason of a zero censored data in this particular example? The experiment only records receptor sequences that are observed at least once. Now, this is the problem. The problem is not that 0 is not being observed. So the sequence that occurs 0 times, it doesn't have any representation in the data. So we never see y equals to 0. So this makes the inference much more difficult, as probably there are many unseen receptor types. So a frequentist approach, a frequentist will assume what? That y follows Poisson lambda, or you may assume y follows negative binomial or any parametric form. So with only 1 or 2 parameters. So everything depends on these 1 parameters. But do we really know that the receptor counts follows Poisson or it follows negative binomial? So instead of going for parametric fitting here, if you can assume that the underlying probability may be a random probability measure, capital F. You can see. So here the black curve, which you can see, is the posterior average, and the gray curves are the random probability measures. Okay, so each draw from this prior will be a probability distribution. This is the idea. Okay, so these are probability distribution over the random probability measure, capital F. Now, so Bayesian non-parametrics can help you in modeling semi-parametric models also. So this example shows that not every unknown has to be non-parametric. Some part of the model can remain parametric, while others can be modeled as non-parametric. So far we have seen 2 extremes. One is parametric model, where everything is described by a finite number of parameters, and another is non-parametric model, where the entire unknown object is infinite dimensional, right? But many practical models lie somewhere in between. So suppose we are studying the survival time of cancer patients, right? Suppose you are studying the survival time of cancer patients. So for each patient, we know age, treatment, tumor stage, they are contained in, suppose, so they are contained in Z, right? So the regression part is, what is the regression part? This is the regression part. It measures how the patient characteristics affect the risk, right? Older patients may have higher risk. A new treatment may reduce the risk in this way. Now the unknown beta, which is finite dimensional. So in this particular situation, this part is finite dimensional. It may have a finite number of parameters which needs to be estimated. Now look at the baseline hazard, lambda naught t. What does it represent? It represents underlying risk of failure over time. Now, do we know the shape of this baseline hazard function? No, we might not know the shape. So it may increase with time, decrease with time, remain constant, or have several peaks. So we don't want to assume that it follows exponential, Weibull, or Gompertz. So lambda naught t, the entire function, is an infinite dimensional parameter space, right? So Bayesian non-parametric methods, as we see in this example, that it is not only used in fully non-parametric models, but also it provides a flexible way to model the infinite dimensional component of semi-parametric models, right? So these are different examples which we can consider where Bayesian non-parametric methods may be useful, right? So now what are the problems or challenges in Bayesian non-parametrics? You need well-defined probability distributions on potentially infinite dimensional spaces. Now, what is the problem? We have till now in Bayesian parametrics, we have defined and interpreted priors on Euclidean spaces, which was much easier. So how to mathematically construct priors on infinite dimensional spaces will be a bit difficult. Also, the intuitive, understanding and interpreting these results is also might be a bit difficult. So the thing is, Bayesian non-parametric, so what does a Bayesian non-parametric CDF estimation look like? So you can see, if you consider all the space of all CDFs, all possible CDFs. So this is clearly an infinite dimensional set. Now, what does a set look like? What is it composed of? It is composed of every point here is a cumulative distribution function. So what are we heading towards? How to define a prior on an infinite dimensional set like this? And once we have data and prior, how to get the posterior? And what are the properties of the posterior? Right. So in this discussion, as I have already said, that we are going to focus on particular problem of clustering or mixture model, and in particular non-parametric models based on Dirichlet process. Okay. So Dirichlet process is like, it's not the entire of or all of Bayesian non-parametrics, but it will help us understand the concept of non-parametrics. So let us focus on the clustering problems. In this clustering problems, we are all familiar with, right? Suppose there are two clusters. So data is generated, it is assumed to be generated according to, suppose, some normal with centering parameter mu of Zn and variance covariance matrix capital sigma, right? Where this Zn, or it can be assumed to be following from categorical distribution rho 1, rho 2, where the rho 1 assumes a proportion of observations coming from some beta distribution, and rho 2 is simply 1 minus rho 1. Right? And as Bayesians need to define priors on the parameters, it can be assumed that the parameters mu k, it follows some normal distribution mu naught sigma naught. Okay. Similarly, if you can have more than two clusters. If you have more than two clusters, then the proportions are generated from, generalization of beta distribution, which is Dirichlet distribution. Okay, so the labels are generated according to categorical distribution with parameters rho 1, rho 2, rho k. Clear? Now, where is the problem? The problem is when you do not know how many clusters are there, or it might so happen that the number of clusters is growing with your data. Okay, as more and more data you are getting, your number of clusters possibility can be more and more. Now you may ask, how is it possible? How is it possible to get growing number of clusters. So you can consider the example of species discovery. Okay, so every day or every week or every month, there are new species which are still being discovered all the time. So when your data is growing, so you haven't yet observed all the clusters here, right? Or you can consider in genetic analysis. So as you see more and more genomes, you might discover more ancestral populations, right? You never know. You haven't yet explored all the ancestral populations which are existing in this globe. Fine. Then in social networks, as you analyze more and more people, or as you analyze more and more social networks, so you can start discovering more and more friend groups or more and more interest groups. So the thing is, when you might have, in this example, if you can see, you might have thousands of clusters. In the last two example, you were dealing with 2 clusters or 3 clusters, known number of clusters. Now, what if the actual number of clusters is thousands and you are observing only, suppose you are observing 100 observations. So you might not have even 100 clusters, whereas the actual number of clusters is 1000. So how in such cases will you understand prefix the number of clusters? It is not possible to prefix the number of clusters. So is it possible to develop a model which will learn the number of clusters from the model itself, based on the data itself? Okay. How much time do I have?
You can take your time.
Okay. So now how to choose the number of clusters in advance? So what are we saying? So in social networks, the number of clusters you cannot say that it is this finite number of clusters, right? In social networking, as you go on analyzing more and more people, you will keep discovering more and more social networks, friend groups. So it can, with your data, so with growing number of data, the complexity of the model will keep increasing and you will keep discovering more and more clusters, right? So the problem is, if you go back to this, so this row 1 plus row 2 here added up to, row 1 plus row 2 added up to 1. Here summation row k will be 1. Now what is, so how do infinite number of proportions add up to 1? Here also you need something which is analogical to the finite number of clusters, right? So how to generate infinite number of, so this was Dirichlet distribution, this was beta distribution, this was Dirichlet distribution, generalization of beta. So what do you do here? How do you conceptualize or generate infinite number of proportions which add up to 1? Okay, so Sethuraman suggested this stick breaking construction. Okay, before Sethuraman, I think Griffiths, Engine and McCloskey, they came up with this proposal of GEM distribution, Griffiths, Engine and McCloskey. Okay, so what is this construction about? How to generate infinite number of probabilities, a sequence of infinite number of probabilities that can add up to 1. So we first consider a stick of length 1. We consider a stick of length 1. Then what we do, we take a random observations generated according to beta distribution with parameter A1 and A2 plus A3 plus A4. Right? And we say that we are breaking the stick of length 1 from this at V1. So we are saying row 1 is V1, right? So what is remaining? Remaining is 1 minus V1. Now what do we do next? We draw another observation randomly from beta A2 comma A3 plus A4. And we are saying, then what do we do? From the remaining 1 minus V1, we break V2 proportion of stick again. And we assign it to the next probability, which is 1 minus V1 times V2. Similarly, Again, we generate V3 from beta A3, A4, and from the what is remaining then? This was remaining. After the second break of the stick, this was remaining. We generate V3 and we cut V3 proportion of this stick which was remaining. So you see, we have broken the stick into 4 proportions which will add up to 1. So this was the idea proposed by Griffiths, Engine and McCloskey to propose a GEM distribution. Now you can see if we keep on taking A1, A2, A3, A4, so what will happen? The number of parameters will keep on increasing. So they put an assumption. Every time they generated a beta from beta 1 comma alpha. Now this alpha is known as the concentration parameter of the GEM distribution. So in this way, you can see if you look at this diagram, this particular distribution is, this is actually, these colors are actually proportions. This entire length is 1. Okay, and these colors are different proportions which we have obtained by using GEM with alpha equals to 3 draws. So what are these? Each of these rectangles, these are draws from GEM distributions. These are random draws. So you can see we already have random probability distributions over rho 1, rho 2, rho k such that summation rho I add up to 1. Clear? So all these are, so now this I have done with alpha equals to 100. See, these have become more dense. The GEM draws have become more dense. So each of these rectangles are a random draw from GEM distribution. Okay, so now we know that how to generate infinite. So if you go on, if you don't just stop with rho equals to, if you don't just stop at rho equals to 3, you can keep doing this. Now, we cannot just do it infinite number of times, but you can choose what k can be. K can be any number which is a large number. Okay, so we will get something like this. You increase alpha, the value of alpha, it will become more dense. Okay, this depends on the property of beta distribution. Now, let us come to Dirichlet process. At least I'll just stop after describing Dirichlet process because I might not be able to complete this thing. So what is a Dirichlet process? So what were we thinking? Again, we get back. So we have random observations, yi, right? These are my data. I assume that my data is generated according to a random probability measure f. So f is my parameter. So as a Bayesian, I will put a prior on my parameter, which is f, the probability distribution itself. So this prior can be considered to be Dirichlet process with parameters alpha and g naught. Where, what is g naught? G naught is a probability distribution. So you see, this is a prior whose parameter is a probability distribution, and alpha is a constant. So what is this probability distribution about? Suppose you have some prior knowledge about what your random probability measure should be. Like suppose you know that, okay, my random probability measure is a continuous distribution and it is symmetric. So you can assume the base measure as G naught. Okay, so this G naught, it reflects your prior knowledge about capital F. And what is alpha? Alpha is the concentration parameter. How alpha should signify how sure you are about your prior knowledge. Clear? We'll see. We'll see. Now, what is the beauty of this Dirichlet process? It can be shown that expectation of this random probability distribution is nothing but the base function. Okay. So how do we, so you may ask, if we draw from a Dirichlet process, how does it look like? So it has to be a random probability measure, right? So how do you draw from a Dirichlet process? Sethuraman in 1994, you can see that this field of Bayesian nonparametrics is a very new field, right? Because Bayesian, parametric Bayesian is existing for more than 100 years. Non-parametric Bayesian we were developing even in 1994 when Sethuraman came up with this beautiful construction, which pretty much summarizes, gives us an idea about how does a random probability draw from Dirichlet process looks like. Okay, so how do we proceed? So you can see some atoms, M1, M2, M4, these are M3, these are atoms. These atoms are numbers which are drawn from the base probability measure G naught. Okay, so if your G naught is a normal distribution, so then these atoms are generated from the base probability measure. Okay, so these are draws from normal distribution. Now, how do you draw these? What are these? These are random probabilities. Probability of getting M1, M2, M3. So how do I get these random probabilities? I get these random probabilities according to this stick breaking construction, which we have already discussed. I take a stick of length 1, I generate V1, the first observation from beta 1 alpha, then I assume that the stick is as if it is broken at V1. So what is this? P1 is this first stick length V1. So this is P1. Right? What is remaining of the stick? 1 minus P1. Then I draw the next draw from beta, 1 comma alpha. Why we have taken 1 comma alpha? For reducing the complexity. Okay, so this much we have borrowed from GEM distribution, right? So again we break V2 proportion from 1 minus P1. See, this is a deterministic transformation of the variables, of the beta random variables. So what is P2? P2 is this. Then what is remaining? We break again V3 proportion from it and name it P3. In this way, we have a random probability measure generated. So these I've generated these distributions from R, using R. You can see for alpha equals to 2. So what are we doing? We are generating from, first we are generating from beta 1 comma alpha. So if alpha is 2, what will happen? The initial the stick length will be longer. So the distribution, you see, it doesn't look very interesting, this distribution. It is concentrated in a few atoms. The entire probability is concentrated in a few atoms. So if you keep on increasing value of alpha, which is known as a concentration parameter of the Dirichlet process, you see here this distribution is, here we have larger number of atoms. So if we keep on increasing alpha, so this is why alpha is known as the concentration parameter. Okay, so if each of these are, this is one draw from Dirichlet process, alpha equals to 2 and G naught, the base probability measure, normal 0, 1. The base probability measure is same here. Just, so these are random draws from Dirichlet process. The idea is when you draw from a random probability measure, it will give you a probability distribution. So these are, so one thing is noticeable here, that the draws from a Dirichlet process will always be discrete probability measures. So Dirichlet process cannot be used directly to, I mean, it's not advisable to use Dirichlet process to directly model continuous random variables. Okay, for that we need to go to Dirichlet process mixture models. Okay, these are alternative definitions of Dirichlet process. So you can just see these are cumulative density functions corresponding to distribution functions corresponding to the same thing, normal 0, 1. This black line you can see, this is normal 0, 0, 1 CDF. And what are these step-like functions? These step-like functions are random probability CDFs from, these are obviously Dirichlet process, we have seen that it is a discrete distribution. So it will be step-like function. So these are random draws. You see for alpha equals to 2, I have, the spread is more against the expectation or the base probability measure. Now, if I increase alpha to 50, you see what alpha equals to 50 says that you have more confidence on your prior probability. So it's dense. So it's concentrated around the base probability measure, right? So, so what should I do? Should I wrap up?
Yeah, you can wrap up in 5 minutes, or if you want to take 10 minutes, you can.
Okay, thank you. So, so you see, why Dirichlet differ? So this is the idea behind Dirichlet process, and you see Dirichlet process prior. So we should not forget why we were using when we started using Dirichlet process. We started using Dirichlet process as a prior distribution. So what are the properties of Dirichlet process prior? One of the most important properties is Dirichlet process prior is a conjugate prior. The posterior distribution, it can be shown that the posterior of the Dirichlet process prior is also a Dirichlet process. I'm not going into mathematical derivation, just trying to share the idea. So this is also, so and you see, this is my data X, which is being generated according to a random probability measure G, where this random probability measure G is generated according to Dirichlet process alpha G naught. So this is a schematic diagram. You see, this data is being generated according to this random probability measure G, which in turn is being drawn from a Dirichlet process prior with parameters alpha and G naught, right? So we have seen that Dirichlet process prior is discrete in nature. So what does that mean? It means that with positive probability, you see, there will always be positive probability alpha by alpha plus m. If you have already drawn m draws, that m plus 1th draw, m plus 1th observation will coincide with with positive probability alpha by alpha plus 1, alpha plus m, it will be a new observation. And with positive probability 1 by alpha plus m, or I mean number of times you have already observed x, it will coincide with one of the observations which has already appeared. So this is the beauty of Dirichlet process, which helps us develop beautiful clustering algorithms in different, which has applications in different machine learning algorithms. Okay. Now, what is the problem of Dirichlet process modeling? Dirichlet process prior. The most important problem is that it is discrete in nature. So what will be the problem? It is not an appropriate prior when the underlying distribution is continuous. So as I was saying, if you want to model a continuous distribution, you need to go for a Dirichlet process mixture model. And how is that? How can we do so? Let us see. So here we assume that yi's are distributed according to a probability distribution characterized by theta. You see, theta I is the parameter. Okay, so if you have multiple clusters, so this is the idea of this is how you can create models over infinite clusters or unknown number of clusters. Okay, using Dirichlet process mixture models. How? So we are assuming that data is being generated according to this P can be normal distribution. Let me come to this. Yeah. So suppose your data is being generated according to capital F. Okay. So this, your data is being generated according to normal distribution with parameters. Normal has finite number of parameters, right? So it is like you have different clusters, and these are the parameters of each cluster. This cluster is being generated from another normal distribution. This cluster is being generated from another normal distribution with different sets of parameters. Okay, so your observation can come from the same cluster also with the same parameter mu I sigma I. Now, how are you going to incorporate that into the model itself? How is it possible? So, if you assume that this parameter, instead of the data being generated according to Dirichlet process, you assume that the parameter is being generated according to Dirichlet process. Do you get my point? If the parameters are being generated according to Dirichlet process, then what is, by the discrete nature of the Dirichlet process? Sorry?
Please continue.
Okay.
Yeah, am I not audible?
You are audible.
Okay. So if you assume that the parameters are being generated according to Dirichlet process, then by the discreteness property of Dirichlet process, what will happen? There is, with positive probability, these two parameters, theta I and theta j, can coincide. And for that, those two observations will belong to the same cluster. So you see, you need not know how many clusters are there. This algorithm will draw you automatically towards the actual number of clusters. So your number of observations can be n. Your number of clusters can be less than that, depending on how your clustering algorithm is taking you to which number of clusters through coincidences by Dirichlet process modeling. Okay. So these are different properties of Dirichlet process modeling. So I'll just mention one example, that suppose we are interested in a simple generative model for English words. And suppose someone asks, what is the next word in a newly discovered word of Shakespeare? Okay, so our model must surely assign non-zero probability for words that Shakespeare never used before. Right, you never know. You have not, suppose there is a new manuscript which has been discovered, and you would like to, and in that manuscript you may discover a word which you never knew that Shakespeare has already used. So Dirichlet process is a model for a what? A stream of symbols that should satisfy the exchangeability rule, and it should allow the vocabulary of symbols to grow without limit. Okay, so with positive probability, you identify each symbol, okay, by a unique integer. So the probability that the next symbol it coincides with one of the words which has already been discovered is positive. And there is positive probability that the next word is something which this author did not use before. So you can go both ways. The next word can be a word which is coincided with the earlier discovered word. The next word can be a word which the author has not yet written. You have not yet discovered. Okay. Okay. So these are some of the examples of Dirichlet process mixture modeling. So I think I would stop here. These are some references. There is this seminal paper by Ferguson. It was published in the year 1973. So the stick breaking construction came in 1994. So I think I will stop here.
Thank you, Dr. Bhattacharya. It was indeed a very informative session based on Bayesian non-parametric. Now this forum is open for any question or discussion. Any question from the participants?
Yeah, would you please mention the reference once again, madam?
Yeah, sure. we have done some work on application of digital process. There are some excellent work. Now it is not very uncommon. You can refer to a book by Peter Muller.
Okay. So just to mention the journal, it is not very small.
Sorry, I couldn't.
Yeah, you put in readable form because.
Okay, it's not readable. Oh, sorry. I shall just a minute.
Don't worry, no problem.
Oh, okay.
Just mention.
Sure. Yeah, I'm not being able to, like. I can share the.
That's okay. Very interesting. Yeah, that's right. So we have to. Yes, it's.
Just a minute. I'll try to share this. This is a book.
No problem. If you can.
Yeah, I think I've chosen the wrong font.
Yeah.
Sorry.
It's no problem. Yeah. Okay, let us. Anyone else? Any questions or anything?
Anyone else want to ask something? Since there is no more query or question, now let me thank Dr. Bhattacharya for sparing her valuable time and for such a very informative talk on statistical learning with infinite dimensional priors, explaining beautifully Bayesian non-parametric and non-parametric two-digit process. Thank you so much, madam.
Thank you so much.
Thank you so much.
Good night, everyone. Thank you.
Good night. Thank you. This is just to inform you that due to some urgent matter, the second speaker of this session, Dr. Manoj Tiwari, is not able to join us today. Now, before closing this session, now I would like to thank all the participants for their patience and attentive learning. A very special thank to Professor Satish Kumar sir and organizing committee of this 11th International Conference for this opportunity and for organizing such a wonderful event every year. Thank you so much.
Thank you, madam. Thank you, Deva madam, for your very interesting and informative presentation. And also, Professor or Neha madam for chairing the session in a very nice way. And we are very much grateful to both of you. And let us conclude this session. And I invite all the participants, including professors. Tomorrow morning session start with Professor Kundu's presentation. Professor Kundu, Somesh Kumar, like that. Yeah. And also Professor T.J. Rao is also. Then we can anyway. Let us conclude today's session. It is a little bit late. Thank you for your patience and support. Thank you all.
Thank you, ma'am. Thank you so much.
Thank you so much. Thank you. Good night.
Thank you, audience. Thank you.
On behalf of the Organizing Committee of WSTA 2026, I extend my heartfelt gratitude to our respected chairperson, Dr. Neha Garg, for her excellent guidance and for chairing this session with great distinction. I sincerely thank our esteemed speaker, Dr. Darba Bhattacharya, for their insightful and inspiring presentation. Your valuable contribution have made this session truly enriching. I also thank all the participants for their active involvement and the organizing team for their dedicated support in making this session a success. Once again, thank you all for being a part of WSTA 2026. Sir, your mic is mute. It's mute.
Thank you all. Please join tomorrow morning before 9 a.m. Okay. by 8:45 itself. Please, all of you join, and also all the delegates, please, especially my students, before you have to join by 8:45 itself. Okay. Okay. Thank you. Good night. Let us conclude the session.